have a house. I don't have a car. So sad, so sad. I don't have money. I don't have money. I don't have money. I don't have a house. I don't have a car. So sad, so sad.
We need to understand what the researchers want, become our requirements, and then we come here and see how we can best meet those requirements, whether they're logistical or operational.
The Earth Science Project Office is in charge of managing the mission. Anything you need to accomplish your objectives during the mission, they are the people to go to.
Entry in a foreign country is very difficult with all the things you're doing. Operating in a foreign country is difficult because their airspace is very busy and maybe some of their procedures are different than ours.
Somewhat of a complicated environment in which to be in. We astronauts, of course, have a lot of things to do. We're aware of the complexity of the environment in which we find ourselves. But if one could develop a platform that could be utilized for, let's say, for tourism, if we wish to use that name, to bring pleasure to those, we could then develop it in that regard so that it would be suitable for that sort of endeavor for leisure travelers, which in some way or other perhaps would not be so different from what we're doing now. It would not be so different from tourism on Earth, for people to go to exotic locations, who live out their spirit of adventure. It's a lot easier to do it now than it used to be, and I suspect that in the future there will be a development that will make space tourism a viable option. Hello, Samantha. I would like to say, physical predispositions or the mental abilities, iron will, resoluteness, resilience, adaptability of the person have more weight in your work? Was it difficult as a woman to be accepted in this working world that is considered more for men by many people? Well, hello. In terms of physical conditions and demands, there are all sorts of conditions of degradation of health that astronauts are forced to face with, even if we're talking about the
James Webb Space Telescope is the follow-on telescope after the great Hubble telescope. It extends the discoveries of Hubble into the infrared spectrum region. We think that the first objects that grew out of the Big Bang material probably happened in about 100 million years after that start.
Hubble gives information that the Webb telescope cannot give about visible and ultraviolet emission from things in the universe. And when we have all that information coming in at the same time, it's like a banquet of scientific return.
Now when we get the complete picture of every wavelength you can possibly see from ultraviolet to infrared, we hope to have the story of the growth of the first galaxies from the primordial material. So that will be a huge accomplishment that depends on both pieces of equipment, the Hubble telescope and the James Webb telescope, working together.
Posing observations with Hubble right now, specifically to help us learn information that will be useful for making the best use of the Webb telescope as soon as it's launched and gets going in its science observations.
I think the Hubble telescope has been the most productive science instrument ever built. In astronomy, there's what we knew before Hubble, and now there's what we know after Hubble. They're so different. Of course, Hubble has now had a life of 30 years, so it's had a long time to make this revolution happen. So it's not all at once. It's a gradual revolution, but it's still a huge revolution. Technology has changed dramatically over the 30 years of life of the Hubble telescope. So you couldn't even have imagined when the Hubble was launched that we would have the wonderful cameras and spectrometers that we fly today. We figured out how to send astronauts. We trained the astronauts. We figured out what instruments could be put in. We figured out how to repair everything that went wrong with Hubble. And it's still alive today, 30 years after launch. And I am so thrilled to say that our people were able to do that. That's the operations team that makes this possible. It's a miracle as far as I'm concerned, because it have to be that way, but they made it happen.
When someone mentions NASA, what comes to mind? Astronauts on the moon? The space station? Rovers on Mars? The Voyagers now flying through interstellar space. But there's no place NASA has explored more than our own planet. NASA has a fleet of satellites that are constantly collecting data to monitor the health of the Earth. Using the vantage point of space to understand our planet dates back to the beginnings of the space age. It was then, in response to the Soviet Union's Sputnik, that JPL built and helped launch the first U.S. satellite, Explorer-1. Inside Explorer was this science instrument, a kind of Geiger counter designed to detect cosmic rays. It also discovered the presence of radiation surrounding the Earth, what turned out to be a belt of charged particles held in place by Earth's magnetic field. They are named the Van Allen radiation belts for the scientist who built Explorer's Geiger counter. This was the very first science discovery made from space. A major finding about our planet, for these belts shield the Earth, deflecting solar particles that would otherwise shred our atmosphere, over time destroying it and everything about our planet as we know it to be. More than half a century has passed since the time of Explorer-1. And today, we know that our planet is changing in ways we need to understand. I'm Mike Meacham, a systems engineer here at JPL. The job of a systems engineer is to look at the big picture of how all different parts of a spacecraft are supposed to interact as one system, and to make sure that they do. The Earth is a system too, with many parts. The land, the ice caps, the oceans, the atmosphere, and living things. I want to discover, along with you, how Earth's complex climate is changing. In the next hour, we are going to explore the role JPL has and is today playing as part of NASA's larger effort to understand what's happening to our atmosphere. But to begin, let's start our journey by visiting the planet known as Earth's twin.
Venus was the first planet chosen to explore for a very practical reason. It is our nearest planetary neighbor. And that proximity offered the best chance for success in the early days of the space age. Still, Mariner 2 barely made it there. At the time of the mission, JPL produced this film, which explored how Venus had once been thought of as Earth's twin, given its smaller size, density, and cloudy atmosphere.
Where does the story start? Historically, I suppose it began more than 100 years ago when man first viewed the clouds of Venus. Because of the thick clouds, it seemed logical to suppose Venus...
There had even been speculation that beneath the planet's clouds, there might exist a tropical world of jungles, swamps, and rainforests. But by the time of Mariner 2, a radically different view of Venus was emerging, due in part to the research of a young scientist who was beginning to make a name for himself, Carl Sagan.
Many theories of the Venus environment have been suggested. However, new information eliminates at least some of these theories. Measurements with radio telescopes show that there is a region on Venus where temperatures are greater than 600 degrees Fahrenheit. It is just possible that the hot region exists at a high altitude. However, it is more likely that the hot region is the surface, heated either by an enormous greenhouse effect or by wind friction. Therefore, if there is life on Venus, it is probably of a type that we cannot now imagine.
Tantalizing, exasperating Venus. A single significant experiment can confirm old or create new theories.
Mariner 2 and the missions that followed did just that, turning Venus into the poster child for global warming. Earth's twin? More like Earth's evil twin. That label was further reinforced when JPL's Magellan spacecraft used radar to penetrate through the clouds and first saw the surface of Venus, a tortured landscape full of ancient volcanoes, more than any other planet in the solar system. Some may still be active. But a billion years ago, Venus may have had an Earth-like climate with oceans of water. Yet over time, something went catastrophically wrong. Volcanoes may have played a role in creating this hellscape that is today's Venus. But the primary cause may be the result of the sun's solar wind. Charged particles that are constantly streaming off our star. The effect of this endless bombardment of radiation weakened Venus's magnetic field, making it unstable and leaving the planet to fend for itself. It may be as simple as Venus wasn't able to handle all this heat. As temperatures rose, the oceans evaporated, turning into water vapor. Then carbon dioxide also built up in the atmosphere, resulting in a runaway greenhouse effect.
With Venus being a little bit closer to the sun, basically meant that it never really had a chance. So over time, that carbon dioxide and water vapor built up. It was impossible for any water to stay on the surface as a liquid. It all stayed in the atmosphere. That produced a massive greenhouse atmosphere that produced a tremendous amount of warming. probably warming even greater than what we're seeing today with surface temperatures around 950 Fahrenheit.
Our next closest planetary neighbor is Mars. Like Venus, the red planet shares similar features with Earth. Mars has polar caps, seasons, and a rotational rate nearly identical to our planet. But any hopes that Mars might have been more Earth-like were squashed after the first flyby of the planet by JPL's Mariner 4. A handful of grainy black and white images from the mission was all that was needed to see that Mars is a barren world. Just like Venus, scientists believe that ancient Mars was more like today's Earth. It was warmer and wetter, wet enough to have had oceans. But about 4 billion years ago, Mars lost its magnetic field that served as a planetary shield. And without the shield, the Martian atmosphere was, like Venus, left at the mercy of the sun's solar wind.
And as it cooled, the interior froze up. And when that happened, the dynamo that generated its magnetic field froze up as well. And that was the end of it for Mars.
It took about 500 million years, but eventually the solar wind shredded the Martian atmosphere. And as it disappeared, the exposed oceans evaporated. And the planet cooled down into the frozen world it is today.
So long ago, Mars and Venus were not just our nearest neighbors, they were our close cousins. Today, Mars is in deep freeze, and Venus is a furnace. Sobering examples of how a planet might flip from paradise to hell.
Are we just lucky that Earth resides in a Goldilocks zone where it's not too hot, not too cold, but just right? That's part of the explanation. But there's also the delicate and intricate balance of interactions taking place throughout our planet's system of water, ice, land, atmosphere, and all living things. The more we learn about these interactions, the more we are understanding how fragile the Earth is to change.
Our planet is warming, and the major causes of that are greenhouse gases like carbon dioxide, or CO2 for short. Carbon dioxide is a chemical compound comprised of 1 part carbon and 2 parts oxygen. The oxygen, not a problem. The carbon, everywhere you look, you're going to find it. It's the basic building block of life. It's in the animals, the fish, the plant, the trees, and in me and you.
Nature has an elegant but simple way of using carbon. It travels from the atmosphere into organisms in the earth, and then back into the atmosphere over and over again. This process is called the carbon cycle. It has helped to keep our climate in balance for at least the last 100,000 years, if not millions. As part of this cycle, carbon from decaying organisms can end up in the ground, where it can be transformed into coal, oil, and natural gas, which we started using as fuels to power machines over 200 years ago. And that changed the natural order of things, as more and more carbon in the form of CO2 is ending up in the atmosphere, where it soaks up and re-emits heat. Have you ever wondered why carbon dioxide and other gases are called greenhouse gases? It's an analogy, of course. A greenhouse works by letting in light, which heats up objects inside a structure like this, keeping plants warm. But if light can get in through this glass, why can't the heat escape back out? The answer is that light and heat are not the same.
The light that we see coming off the sun is just a sliver of the electromagnetic spectrum. Energy that ranges from very long wavelength, like radio waves, to shorter wavelengths, like X-rays. The wavelength that we can pick up with our eyes is a relatively shorter wavelength of radiation that can penetrate through this glass. Heat, in the form of infrared radiation, has longer wavelengths, and it can't travel through the glass as easily. The result? The greenhouse warms up. CO2 in the atmosphere works in a similar way. It slows the heat escaping out into space, and the result? The Earth warms up. Across the globe, humans output about 40 million tons of CO2 into the atmosphere every year. But let's turn that number into something more down to earth.
Let's say the average car weighs about 2 tons. So we, the world, by burning fossil fuels in various ways, are putting the equivalent mass of 20 billion cars into the atmosphere every year. And the lifetime of CO2 in the atmosphere, hundreds of years. With nearly every passing year, the level of CO2 is rising. In 1950, the record for the highest amount of CO2 that had stood for 800,000 years was shattered. Since then, the spike has soared. And now the Earth is heating up at the fastest rate of any known time in the history of our planet. The last time CO2 was this high was nearly 4 million years ago. A time when sea level was 78 feet higher than today, and the Arctic was covered with forests. The importance of CO2 and other greenhouse gases was not lost on scientists at JPL. One of them was Mustafa Shaheen, a native of Lebanon who moved to the United States to attend college. In 1958, while pursuing his PhD at UC Berkeley, he saw in the news the iconic image of JPL's Explorer 1 being held aloft. That moment inspired him to pursue a space career, which took him to JPL. Moose, as everyone called him, was as non-assuming as he was brilliant. He served as JPL's chief scientist, and it was largely his idea to create an organization to harbor and nurture the lab's growing number of scientists.
For outstanding performance and leadership in developing the JPL Earth and Space Sciences Division and enhancing the science programs of JPL and NASA. Mustafa T. Shaheen.
Moose's motto was, always make progress. And for 3 decades, Moose was fixated on finding a way to study Earth's atmosphere from the vantage of space.
The value of satellite data is that it gives you global coverage. Now we can get global coverage with the same accuracy as balloon-borne instrument.
Moose's ambition was to build a science instrument that would help to understand climate change. But that proved to be a hard sell politically. So he stressed how the same instrument could also be used to improve weather forecasting.
The mission is to understand the relationship between weather and climate. For example, are the weather anomalies, which we are seeing today, hurricanes, etc., are they related to climate change?
And for that idea, he found takers. Moose's instrument, called the Atmospheric Infrared Sounder, or AIRS, was one of 6 science instruments that won a spot to fly aboard NASA's Aqua satellite. AIRS was designed to detect infrared energy over a range of more than 2,000 wavelength bands. And from those bands it was hoped, for AIRS was officially an experiment, that it would be possible to create 3D maps of atmospheric temperatures and water vapor. But before any of these measurements could be put to work, all of the raw data of zeros and ones first had to be calibrated and validated.
Once you have those numbers that you think represent reality, you have to confirm that they are reality. This is one thing I did for the first 5 or so years of the mission, pretty much daily, including a lot of weekends. Just looked at what AIRS said and what, say, a weather balloon said. Or what AIRS said and what an aircraft that flew underneath AIRS said. And with several years of hard work, we concluded we weren't crazy, that the numbers that we reported from the instrument were actually representative of reality.
And soon, AIRS began delivering on its promise. Its measurements were helping to improve weather forecasts.
That was said to be enough to pay for the instrument itself. So forecast really was a major accomplishment. But NASA's not a forecast center.
And Moose, always trying to make progress, next wanted to explore how AIRS might be put to use to better understand climate change.
As part of AIR's original purpose of improving weather forecasting, the instrument had already gathered a wealth of data about water vapor, which is H2O in the form of an invisible gas. We know it best as humidity.
Water vapor is also a greenhouse gas. And there's more water vapor than all other greenhouse gases combined. But through the ages, the warmth provided by water vapor has been a good thing. Without it, our planet would be just a frozen ice cube. Water vapor is part of nature's normal recycling of water from the Earth's surface into the atmosphere, and then back again to the surface. And this recycling goes on constantly, but on different timescales. A piece of ice in the Arctic can remain a solid for millions of years. A drop of water in the ocean, thousands of years. That same drop of water, in the form of water vapor in the atmosphere, on average, just 9 days. The amount of water vapor in the atmosphere is directly related to temperature. The warmer it is, the more water evaporates, becoming water vapor. And more water vapor results in warmer temperatures.
So you've got here a cycle. When you change the state of water from vapor to liquid, this change releases enormous amount of energy into the atmosphere. Understanding it is critical to understanding our climate change. This is why it is important.
At any one time, the atmosphere contains over 37 billion gallons of water vapor, which contains an astonishing amount of energy. And all this water vapor doesn't disappear into thin air. It is constantly transforming back into water, ice, and snow, which rains down on us. Often in the form of storms that are becoming more frequent and more severe. But water vapor is not the driver of global warming. The main catalyst is carbon dioxide, CO2. And Moose wanted to tease out of the AIRS data the signature of CO2 and other greenhouse gases, which he nicknamed the culprit. But detecting CO2 from the data proved an enormously difficult task, what his team likened to unscrambling a scrambled egg.
So the problem here is looking at a set of data with the information you want, and the noise is so high that what you are looking for is within the noise. The unscrambling of a scrambled egg. That difficulty was thought of as unsurmountable.
But just 4 years after the launch of AIRS, the insurmountable was surmounted. The culprit, Moose declared, had been coaxed out of hiding.
We've done it, now we are looking at climate.
This is the first global map showing the distribution of carbon dioxide around the world as seen from Earth orbit. It clearly shows a distinct pattern of high carbon dioxide in the northern hemisphere, which was consistent with predictions made by climate modelers. Methane, another greenhouse gas, is seen here having a global distribution similar to that of CO2. Here, carbon monoxide, which is not a greenhouse gas, can be seen being created by the burning of forests in the Amazon. The gas then makes its way across the Atlantic. Fires in Africa can also be seen. This animation is composed of nearly 6 years of AIRS' first observations. The overlaying of the up and down curves are CO2 measurements made from the ground that correspond to the seasons. It is a way of showing how the Earth breathes. Note the steady march of CO2 upwards. The map continues to be updated, all showing a constant increase of CO2. 20 years after being launched, the AIRS instrument on board NASA's Aqua satellite is still operating, eyeing from Earth orbit not only greenhouse gases, but hurricanes, dust storms, wildfires, volcanoes, and of course, helping weather forecasts. It was a kind of progress Moose had always hoped to accomplish.
It is like having worked for an idea. And I had doubts, my colleagues had doubts, but 30 years later, the idea works. And this is the great sense of happiness, of satisfaction I get and my colleagues get out of this. That a concept that we worked on for 30 years worked, and worked very well. This is great.
The pioneering success of AIRS helped to create a pathway for CO2 hunters that followed. Here at JPL, a handful of scientists plotted out a new mission, the Orbiting Carbon Observatory, or OCO. It was envisioned as an instrument to fly on a spacecraft devoted solely to measuring carbon dioxide.
The goal was to learn where CO2 was being created, what are known as sources, and where it was being absorbed, sinks. It was already understood that half of the CO2 was being absorbed into the atmosphere, leaving the other half going into sinks in the oceans, forests, and the land. Exactly where and how much were unknown, but OCO intended to find the answers, adding a new dimension of data on top of what AIRS was providing.
AIRS measures CO2 at high altitudes in the atmosphere, about halfway between where we're sitting on the ground here and where airplanes fly. And so it was a useful measurement for studying the impact of carbon dioxide on greenhouse effects, but it wasn't useful for actually tracking the sources that were emitting carbon dioxide into the air and the natural sinks that are absorbing it at the surface. For that, we needed to use reflected sunlight rather than thermal energy to make this measurement, and we can essentially count all of the molecules from the top of the atmosphere down to the surface and back to space. That measurement's much, much better for tracking CO2 sources and sinks.
In 2002, the mission was given the go-ahead by NASA By then, scientists everywhere were realizing that climate change wasn't something far off in the future. It was going to impact their children's lives, if not their own, which made the work of the OCO team even more urgent.
The original Orbiting Carbon Observatory mission was a long, difficult project. It took 9 years of effort, 1,000 work years, a lot of trials and tribulations to get to the launch site. So on February 24th, 2009, we were finally there.
Check 130, verify all nose arms and scissors. Check 131, RSCLC, send range status and alert signal, verify.
It was indeed a beautiful evening. You can clearly see the stars in the sky. There was very little wind. So it was a perfect night. The air was just filled with excitement.
RSCLC, step 132.
So we went through the manuals and made all our final checks, and I gave the go-ahead, saying that, yeah, OCO is ready to launch, and I remember the countdown being given, 10, 9, 8,
7, 6, 5, 4,
3, 2, 1,
0. Liftoff of the Taurus rocket with OCO, tracking a greenhouse gas in seek of clues to global warming.
All of your senses are heightened, your emotions are running on overdrive. All of those years of work is finally leading up to this culmination. We could hear the rumble inside of the control room.
Attitude nominal, attitude nominal.
Not just glued to our chairs, but also glued to the monitors.
0 TVA initialized, pressure nominal. Second stage 1 ignition in approximately 5 seconds.
It was a beautiful launch.
Vent cover jettison. Stage 0 burnout, stage 1 ignition, stage 0 separation. Vehicle attitude nominal, power buses nominal. Stage 1 burn will last approximately 70 seconds.
You couldn't have asked for anything better.
Because the sky was so clear, we could actually see the rocket go all the way to the horizon, just with our naked eyes, and we got some beautiful pictures of that. Everything went perfectly up until 3 minutes and 50 seconds after the launch.
Bearing separation. Vehicle attitude nominal following jettison of payload fairing. Proper load shedding.
We were listening intently on our headsets, and then I heard some chatter.
Vehicle is... What's that?
But I was also looking at the screen. The animation was still showing everything was fine, but my eyes were telling me one thing, but I was hearing something different.
I was in the control center, standing at the screen, watching the numbers go by, and I knew that to make orbit, I had to go 7 kilometers per second. And every calculation I could do in my mind at 2 o'clock in the morning was telling me those numbers weren't adding up. So I turned around to the main engineer for the rocket, and I kind of went like this, and he goes, "I'm sorry."
NLMnet. It appears we've had a contingency with the OCO mission. Please enact the mission mishap preparedness and contingency plan. Begin with notification, data impoundment, and mishap response tasks. Do not leave your station. Do not attempt to call out and release information to anyone or speculate on the cause of the contingency.
It was devastating. Everything seemed so surreal. We kept looking at this plume from the second stage, and we're hearing all this chatter on the engineering net, and it just didn't make sense. It was just this sense of disbelief and shock.
NASA's orbiting carbon observatory satellite failed to reach orbit after its 1:55 and 31-second launch time liftoff from Vandenberg Air Force Base.
It only took a few hours to determine what had happened.
Preliminary indications are that the fairing on the Taurus XL launch vehicle failed to separate. The fairing is a clamshell structure that encapsulates the satellite as it travels through the atmosphere.
The fairing, the pointy end on the rocket, was supposed to open up. That didn't happen. The mechanism that was supposed to open the fairing failed, malfunctioned. And so the fairing stayed on the rocket.
Instead of reaching orbit, the spacecraft, still encased in the fairing, re-entered the atmosphere and fell back to Earth.
So, it was like losing somebody you've loved. It was that emotional for all of us. But I would say 24 hours later, those emotions turned into a resolve.
But along with resolve, to refly the mission required new funding.
This was not an easy time to try to go back and refly a mission that you had just lost. We had just dropped $250 million in the Indian Ocean. We were going to go to Congress and the White House and say, can I have some more money to do it again? This is hard to do at any time, but it was especially hard to do in February of 2009 because we were in the depths of the greatest recession since the Great Depression.
It took a year to get the NASA funds to rebuild the mission, which was named OCO-2. But the funding ended up being delayed. Keeping the team intact while marking time became a new challenge.
7, 6.
Then NASA suffered the loss of another spacecraft. The Goddard Space Flight Center's Glory mission, like OCO, was launched from the same launch site on the same type of rocket.
We're at T+300 seconds. The vehicle speeder is indicating underperformance.
And met the same fate for the same reason.
Which is expected due to a fairing not separating.
The loss of Glory caused further delays for the launch of OCO-2.
Do not leave your stations until release. Do not attempt to call out and release information to anyone or speculate on the cause.
Years passed before the cause of the Glory and OCO fairing failures was tracked down. But in 2019, the U.S. Department of Justice announced that a manufacturer whose materials had been used in the fairing release mechanism had agreed to a fine of $46 million to resolve criminal charges and civil claims related to falsifying test certifications. 5 years after the loss of the first OCO spacecraft, the second orbiting carbon observatory was sitting on the launch pad.
At T-minus 1 hour, 38 minutes, 8 seconds and counting, this is Delta Launch Control.
We knew we had built an OCO-2 that was going to work, and I felt a lot of excitement. It was a beautiful launch, but it was a one that we didn't see.
On this night, Vandenberg Air Force Base was fogged in. Not that anyone really cared, for OCO-2 would be treated to a perfect ride.
Engine start.
We're lift off of the Delta II rocket with OCO-2, tracking a greenhouse gas in seek of clues to climate change.
So I remember one of my colleagues saying, "Hey, wow, that was one of the best launches I never saw."
The chamber pressure in the
3 solids, good symmetrical burn. 22 seconds in, still looking good. Good chamber pressure on the second stage. Standing by for fairing jettison. And we have fairing jettison. Standing by for SECO 1, standing by. And we have SECO.
I mentioned to a lot of you that we wanted an opportunity to finally complete some unfinished business with the loss of the original OCO mission, and we've taken the first step in that direction. Solar arrays did deploy, and we are power positive.
And now OCO2 was circling the Earth 14.5 times every day, and completing a full mapping of the Earth every 16 days, making millions of individual measurements that now had to be translated into usable data. But OCO2's challenges were not over. After calibrating the instrument, scientists thought something was wrong.
There was a problem when we recognized that the light signals of the glint data over the ocean were not nearly what we thought they should be. On the land, that data was looking really good. But when you look over the ocean, you're looking at where the bright sun glint is. We were starting to analyze that data. The retrievals weren't looking good. And then one of our guys had plotted this as a function of the angle of the sun. And he says, there's a certain pattern I expect I'm going to see, and I'm not seeing that pattern. I know this idea is kind of crazy, but this data sort of looks to me like you're measuring with the wrong sensitivity to polarization. And just to clarify what polarization is, we probably all have a pair of sunglasses. And if you have polarized sunglasses, when you look at a piece of water, right, it's not super glary. And if you turn your sunglasses 90 degrees, you would actually see the glary light again. So it's very different at this 90 degrees off, especially over water reflections. So he's like, I think we've got our sunglasses on sideways. We're looking at the wrong polarization. And we're like, are you serious, Chris? We're both like, are you serious? And we're like, uh-oh.
The problem was traced back to an error in the design of the science instrument, a flaw that could not be fixed with spacecraft in orbit.
This is where the engineering team again saved our bacon, and they found that in fact we could just fly our spacecraft a little bit angled. It was not such an angle that the sunlight wasn't enough, so the solar panel still got enough light. It wasn't 90 degrees to get that full sensitivity, but it was a third of the way there, and it actually increased the signal enough. In the end, right, I can make it all sound like, oh, simple solution, rotate your spacecraft. There was a lot of angst between, I think our sensitivity is different, and here we go with our little rotated spacecraft. But yeah, wow, that was quite a start of a mission.
Then a new problem arose. Following the loss of the Glory mission, OCO2's launch was delayed for more than a year, forcing the spacecraft to be put into storage, and that had unforeseen consequences.
While we were in storage, unknown to us, the focal planes, the detectors that detect the light, the infrared light, were slowly pulling themselves apart because they were at room temperature and they wanted to be really, really cold, halfway between room temperature and absolute zero. And so when we flew the mission, many of the detector pixels across our infrared focal planes had gone bad. So it's just another challenge. We still had plenty of pixels that work. The question is, how do we work around the ones that went bad? We calibrated a whole set of data, we ran it through computers. It took months and months of processing, and products that came out weren't good.
The scientists were forced to scrub through their data a second time. And remember, OCO2 is beaming back about 1 million individual measurements, or soundings as they are called, every single day. That's 24 soundings a second. And most of them, like those taken at night over clouds and those bad pixels, are of no use. They have to be filtered out. So by the end of every day, the team has about 85,000 usable soundings. Yet even with a really fast computer, it takes about 5 minutes of computation time per sounding to derive any useful information. And to do this, thousands of computers have to be lashed together. And the CO2 that scientists are seeking to find in the data is absolutely minuscule, about 400 parts per million. Which means detecting 400 CO2 molecules residing in the midst of 1 million other molecules. It's enough to bring even a supercomputer to its knees. It all points to the fact that we're now in a different space age. Coping with these massive data sets is now as much or more of a challenge as creating the rockets and science instruments that are now being flown. And to the dismay of the OCO2 team, their measurements still weren't adding up.
So there was an early version of our OCO2 data that we don't even like to talk about amongst our team. A math calculation got put in the wrong order, and the subset of data we were testing with this error was not obvious. But once we gave it to the data processing team and they started running through a year of data, you built up a time series and you could really see, oh, something is not right in this data set. You don't imagine some of these things that could be happening, and so you'd not imagined it, you didn't test for it, and you didn't see it, and there you go, it shows up, and then you're like, oh, completely missed that one. In hindsight, I've gone through this process so many times over, I'm like, oh, that's par for the course. But it was my first time with delivering a big data set, being one of the key responsible members, and I was just like, holy cow, I can't believe we did that.
The team, which had been working 24-hour days, regrouped, came up with a different solution. And that solution worked extremely well. And then we were able to reprocess that data to derive CO2 values that have basically led the world in precision and accuracy.
But surprises with the OCO's data results, what scientists call end products, kept on coming. The biggest of them came from Mother Earth herself.
By the spring of 2015, just as we're starting to get a useful product out of it, we started realizing the product was not looking quite like what we expected. We expected a product that showed us that tropical rainforests were the lungs of the planet. Then we expected them to be where CO2 was being pulled out of the atmosphere by those marvelous trees and plants all the way across the tropics. We weren't seeing that. We saw that the Amazon is actually emitting carbon dioxide into the air, not absorbing it.
The Amazon, the largest rainforest in the world, has been known to be a major absorber of CO2. So what had caused such a profound shift?
Thought, oh my gosh, biomass burning, fires, wildfires are burning in the tropics, and that's adding carbon dioxide to the air. And that turned out being a tiny piece of what was actually happening.
What else was happening was an intense El Nino, a climate pattern that causes an unusual warming of waters in the Pacific. And this El Nino was also warming the Amazon.
They had been going through years of drought. And the extra drought and heat associated with the El Nino just basically shut the trees down. They stopped photosynthesizing. They stopped even trying to grow. And because of that, they stopped absorbing carbon dioxide like they usually do. But that was just the Amazon. In Africa, they had plenty of rain. But it was incredibly hot, the hottest temperatures they had seen. Plants actually absorb carbon dioxide through photosynthesis, but they release carbon dioxide through respiration. And because of the higher temperatures, the respiration was outstripping the photosynthesis. Then we had Southeast Asia. And in Southeast Asia, Indonesia, it was fire. The fires were burning out of control. We got to watch all of this happen with OCO2 and make detailed measurements of how the land biosphere, these trees, were interacting with the atmosphere.
With all of these tropical forests emitting rather than absorbing CO2, it would seem that the amount of carbon dioxide in the atmosphere would skyrocket. But that had not happened. Instead, for some reason, CO2 was being absorbed someplace else. But where?
Well, it turns out that most of it looks like it's going into northern hemisphere forest. So the forest across Europe, across Asia, across North America. So we're still tracking that down because it's not going into those forests uniformly. Some of those forests are burning down. You hear about the giant fires across Alaska or across Siberia. That's emitting carbon dioxide, but yet the forests around them are growing. And why are they growing? Well, climate change. As the climate has become warmer, the growing seasons have become longer. The number of trees and the size of the trees has been increasing. So a lot of things are happening with climate change that are changing where the sinks are going. It could have been that when we originally wanted to launch OCO back in 2009, that the tropical forests actually were absorbing CO2. They're not now.
Scientists do not know how long the northern forests will be able to carry the burden of absorbing CO2. But we do know more about the health of forests, thanks to OCO2. That's because scientists have been able to tease out of the data the fluorescence of plants. This faint glowing, invisible to the naked eye, is a natural part of the healthy photosynthesis process. The kind of energy being emitted can tell us much about the condition of forests, plants, and even crops. This bonus science was one reason why a third OCO instrument was built out of leftover spare parts. But OCO3 is not a carbon copy of OCO2. Instead of flying on a spacecraft, it was designed to be installed on the International Space Station in 2019. OCO3 can be thought of as a kind of point-and-shoot camera, which gives scientists more flexibility in zeroing in on areas of interest. And among those targets are large cities. Urban areas account for more than 70% of all greenhouse emissions caused by humans. These are scenes of Los Angeles, which has the 5th largest urban carbon footprint in the world. It's one of the many urban areas around the globe that OCO3 has set its sights on. With a single pass over the Los Angeles basin, OCO3 can take snapshots that can reveal tiny differences in levels of CO2 throughout the area. The highest readings, in yellow on this map, are on the west side of downtown LA, a densely populated area with congested freeways and CO2-emitting industries. The amount of CO2 being emitted there is about twice the global average.
Los Angeles has an ambitious plan to become carbon neutral by the year 2050. That will be no easy task. But having the ability to track CO2 emissions from the ground, the air, and from space will be crucial in understanding the path forward, for there's a lot of unfinished business ahead of us.
We've not touched upon ozone yet, and here there's an encouraging story from the past that can help to guide how we choose to confront climate change in the days ahead. At the beginning of our journey, we saw that JPL's Explorer-1 mission discovered the Van Allen radiation belts that protect our planet from harmful solar radiation. And it turns out our planet has a second line of defense, the ozone layer in the upper atmosphere that acts as a sunscreen, blocking ultraviolet rays that would otherwise sterilize the Earth and damage all living things. But back in 1985, the surprising results of a British expedition to the Antarctic landed like a bombshell. The discovery of a dramatic drop in the amount of ozone gas at the southern pole, what came to be known as the ozone hole. This discovery raised all kinds of questions. Was the hole an aberration? Why was it only at the South Pole? Was it spreading? And if so, how long would it be before the hole reached populated areas? An urgent concern was knowing what was causing the ozone depletion. Theories abounded. Might there be a natural explanation? Or was it human-caused? The United States rushed a scientific expedition to the Antarctic the very next year. The team included JPL scientists who deployed on the ground a science instrument originally designed for high-altitude balloon observations. Their results, and those of other measurements made on the expedition, pointed to a human cause for the hole, a class of chemicals called chlorofluorocarbons, or CFCs, that were being used in everyday products like hairsprays and air conditioners. In the years that followed, many more types of ozone measurements were made, many of them by JPL teams who used balloons, aircraft, satellites, and the space shuttle as platforms for their instruments. Early on, many nations of the world, alarmed by the news that CFCs were destroying the ozone layer, quickly agreed to address the problem by signing the Montreal Protocol. This international agreement called for reducing CFC emissions by half and later called for a complete ban. It is the only UN treaty that has ever been ratified by every country on Earth. And today, the ozone hole is healing. Based on current projections, a half century from now, ozone in the atmosphere will return to healthy levels once again.
What's being done to tackle ozone is a model, a roadmap for addressing the greenhouse gases that are warming up our planet. But make no mistake, this will be a much harder and longer road for the world to travel than ozone. Remember early on when we met that young scientist who shared his findings about what greenhouse gases had done to Venus? 2 decades later, in 1985, Carl Sagan would again address the impact of greenhouse gases, but this time it would be about our planet. His words are as true for us today as they were then.
We have a kind of handwriting on the wall. The power of human beings to affect and control and change the environment is growing as our technology grows. And at present time, we clearly have reached the stage where we are capable, both intentionally and inadvertently, to make significant changes in the global climate and in the global ecosystem, because the effects occupy more than a human generation. There is a tendency to say that they are not our problem. Of course, then they are nobody's problem. We are passing on extremely grave problems for our children, when the time to solve the problems, if they can be solved at all, is now. It is also a global problem. The nations, to deal with this problem, have to make a change from their traditional concern about themselves and not about the planet and the species. A change from the traditional short-term objectives to longer-term objectives. I think that what is essential for this problem is a global consciousness. A view that transcends our exclusive identifications with the generational and political groupings into which by accident we have been born.
We are all on this planet together, and the path forward will take all of us working together. I'm Mike Meacham. Thanks for watching and for taking care of the good Earth.
Cold, there's polar bears, there's water that can open up underneath your feet. And so it was a very interesting experience to be on the ship, which was very safe and warm and felt good. But then we'd go out and we'd do our field work and we'd set things up and we'd be out on the ice, and you could feel like this is a very wild environment. As we were transiting through the ice, we were searching how big the flows were, but what we didn't know is how thick they were. We went to some of these flows and we found, though these are really thin, we can't actually use this flow. We looked at some ISAT-2 tracks in hopes that some of the flows that we had identified, we could see how thick they were. It didn't work out this time, but for a future expedition, I think we've identified ways that we could utilize ISAT-2 or something like ISAT-2.
Methods to measure other aspects of our planet, like forests. So, why take measurements of the same thing using different methods? And how does measuring sea ice thickness relate to tree height? Let's take a closer look at the Ice, Cloud, and Land Elevation Satellite, or ISAT-2. Its main purpose is to measure ice thickness using its sole instrument, Atlas. But it also measures tree heights as it orbits Earth. This is done with photon-counting lasers and algorithms developed to differentiate what environments they are measuring. An algorithm is a step-by-step procedure for solving a problem, usually a mathematical one, in a limited number of steps. Claudia Caraballo was the deputy lead for the Flight Science Receiver algorithms, one of many subsystems of the Atlas instrument.
The algorithms that process the data on the ground for ISAT-2 are tailored directly to address that characteristics of the surface. So they are tested against all the data as you're processing.
When I was on Mosaic, we took specific measurements that are useful and will be used. By combining multiple measurements together, we're able to quantify and see whether ISAT-2 is making its measurements accurately and how it's needed to be done.
The ways that you can actually figure out if ISAT-2 is actually measuring the right thing is to compare it with observations that are being collected by other means.
Right. Comparing how the instrument works. Dr. Laura Duncanson uses LiDAR data to create 3D maps of forests, and Dr. Nancy Glenn is currently looking at various ways in which tree height data collected by ISAT-2 and Globe observers can be utilized. For both, tree height data adds to our understanding of Earth's systems.
Of course, we can't go out into the woods all over the planet and measure every single tree on the ground. So for ISAT-2, these estimates of tree height, we don't know exactly how precise they are or how good they are in all of the different forests around the globe. There's a lot of variability in forests.
Just like how taking field observations and airborne data collected of sea ice thickness can act as supplementary data to ICESat-2, tree height measurements collected in the field can also be used to do the same. This supplementary data can help scientists account for variability between different environments when looking at measurements collected by satellites. As mentioned, tree height measurements can be taken in different ways. One method is to use trigonometry to estimate the height of a tree.
Having people go into the woods and actually measure tree height to compare.
Using different methods can help scientists. Taking tree height measurements adds a whole new data set for satellites and instruments such as ICESat-2 and JEDI to compare with. These measurements also provide content that only an observer on the ground can provide.
There aren't forests, but we've never before known how tall the trees in those forests are. And this is a really critical piece of information because it tells us not only, of course, how tall the forests are, but how much above ground woody carbon they store. Forests represent one of the biggest carbon stocks on the Earth's surface. And if we cut down and burn forests, we essentially are pushing more carbon into the atmosphere. And if we allow those forests to regrow, we're sucking.
It only helps scientists track how much carbon is getting released into the air, but can also be used in other ways.
Tree height is really important for us is that we're interested in knowing how tree height is affected by increased CO2 or increased temperatures or decreased temperatures. And that gives us an indicator for making predictions about trees in the future. We're interested in is that trees and the differences in tree heights provide some level of what we call structural diversity. And structural diversity can be really, really important for a health of an ecosystem, as well as provide habitat resources, NASA airborne data, as well as satellite-based data like ICESat.
Many Earth-observing satellites, such as Landsat, can only see a top-down view of Earth. This information comes in the form of two-dimensional images made up of pixels between the size of 30 meters squared to 500 meters squared. But now, with JEDI on board the International Space Station and the launch of the ICESat-2 satellite in 2018, scientists are able to see height added to this top-down view of Earth. By taking and submitting tree height observations, citizen scientists and students can help scientists and researchers, not just by providing measurements from different ecosystems, but by providing it can help scientists across the world.
Tree observations essentially let people all over the world measure tree heights and give us that information where we can't go into every single forest ourselves as a small group of scientists.
When a scientist participates in citizen science, it's a great intersection. The more data, the better. But also the connection, right, is that the connection between scientists and the community, and scientists understanding what's important to our communities and being able to engage and learn from one another.
There is a large part of collaboration between the instrument scientists and everybody working on every aspect of the Atlas instrument, and the mission scientists and his deputy and everyone else in all the universities. Citizen science is really important to get the community involved, to motivate everybody to be more informed about the science, and also perhaps motivate graduate scientists.
All of this is important because one, it's the pursuit of answering questions about our natural environment. Our natural environment is changing very rapidly.
A tree height measurement that's taken by citizen scientists could be useful for us.
It's really important for us to monitor what is here now so we can document that, but also use that in models to predict what might be here in the future.
To learn more about Globe Observer, check out the website.gov and download the app to start taking your own observations today.
Today, GPS and similar navigation systems use satellites in space to help you navigate where you want to go here on Earth. Tomorrow, these same satellites will transform navigation in space, as well as making life on Earth safer, healthier, and more productive. And they will even help navigate missions to the moon and spacecraft on the way to Mars. This will be accomplished through the international collaboration and capability called the Space Service Volume. Worldwide, there are 4 global navigation satellite systems and 2 regional navigation satellite systems, collectively known as GNSS. These navigation constellations include the United States' GPS, Russia's GLONASS, Europe's Galileo, China's BDS, India's NAVIC, and Japan's QZSS. Individually, these constellations significantly improve navigation for spacecraft in low Earth orbit, like the International Space Station, or missions that measure climate change and map the Earth's surface. But for the spacecraft located called the Space Service Volume, navigation is more challenging. The Space Service Volume stretches from 3,000 to 36,000 kilometers above Earth. Most navigation satellite orbits are inside this region and broadcast their signals toward Earth. However, it is challenging for other satellites, like weather or communication satellites at the top of the Space Service Volume to receive these signals. Users on the other side of Earth receive weaker signals from navigation satellites because of longer travel distances. Additionally, the Earth blocks most of the navigation satellite's signals. In response, engineers have developed a special technology to navigate with weaker and fewer signals in view. But this does not overcome all of the challenges. Because users in low Earth orbit are below the navigation satellites, the individual constellations can guarantee lots of signals for missions like space station. In the upper reaches of the Space Service Volume, users receive significantly fewer navigation signals and many times no signals at all. If all navigation constellations are able to operate together, signal reception dramatically improves with an average of 4 to 12 signals continually. This is critical to ensure navigation support 24/7, 365. This unified system is called the Multi-GNSS Space Service Volume. Working together. The International Committee on GNSS, the ICG, sponsored by the United Nations Office of Outer Space Affairs, is leading collaborative efforts to ensure that all of these systems are interoperable through the creation of common definitions and specifications. Operating together, this combined system of navigation satellites will be transformational for missions operating within and above the Space Service Volume, significantly improving navigation performance and enabling spacecraft to navigate autonomously without any direction from the ground. This technology enables accurate pinpointing of extreme weather, like flash floods, tornadoes, and hurricanes, crucial for public safety and more accurate weather prediction. It will fuel future advancement in observing, communicating, and working in space, even extending all the way out to the moon. Like GNSS has transformed our lives on Earth, navigation in space will enable scientists to devise exciting new missions, improving science and enhancing our life on Earth, all via the Multi-GNSS Space Service Volume.
What's up for June? A planetary breakup, prime viewing for a well-known star cluster, and the constellation Lyra. The gathering of 4 naked-eye planets we've been enjoying in the morning sky for the past few months, including several close conjunctions, is beginning to break up. Over the next few months, Saturn, Mars, Jupiter, and Venus will appear increasingly spread out across the morning sky, so much so that Venus and Saturn will make their exits as morning objects for most observers by September. Look for this increasingly spaced-out planetary procession in June and note that the crescent moon jumps into the lineup on the morning of the 23rd. June is an excellent time to observe one of the best-known globular star clusters, M13, also known as the Hercules cluster. Globular clusters are spherical collections of stars tightly packed together in their centers. M13 itself contains several 100,000 stars. Globular clusters are also extremely old. The stars in M13 are thought to be around 12 billion years old, which is approaching the age of the universe itself. Our home galaxy, the Milky Way, is known to have about 150 globular clusters, disk traveling tens of thousands of light years above and below its spiral arms and most of its stars. Now, the Hercules cluster is best observed with a telescope, and larger telescopes will allow you to see more of the cluster's stars. But you can also Find M13 in the constellation Hercules, which is high in the east in the first couple of hours after dark in June. First look for the bright stars Vega and Arcturus. Then find the 4 stars that comprise the keystone, which is the pattern making up the central part of Hercules. You'll find M13 about a third of the way between the 2 stars on the western or leading side of the keystone. So check out the Great Globular Cluster in Hercules, M13 in June, and find yourself staring at an ancient gathering of stars that soars high above the Milky Way. Finally in June, a quick introduction to one of the smaller constellations that's home to one of the brightest stars. That's the constellation Lyra. It represents the musician Orpheus in Greek mythology. In Arab cultures, as well as ancient Egypt and India, Lyra was seen as an eagle. And the Inca of South America saw it as a llama. Find Lyra by looking for Vega, which is the westernmost of the 3 bright stars in the summer triangle. In the northern hemisphere, you'll find it halfway up the eastern sky in the first couple of hours after dark in June. Vega is by far the brightest star in Lyra. It's the 5th brightest star in the sky and the 2nd brightest in the northern hemisphere after Sirius. A pair of binoculars will help you see the other stars in Lyra, which form a sort of parallelogram hanging beneath it. It's sometimes described as looking a bit like a diamond ring, with Vega as the diamond. And that's not the only ring in Lyra. It's also home to the famous Ring Nebula, where a star has blown off most of its outer layers, leaving behind a remnant star known as a white dwarf. So let the bright star Vega lead you to Lyra, the Harp constellation in the June sky. And if you see it as an eagle, or a diamond ring, or a llama, well, that's perfectly okay too. Here are the phases of the moon for June. Stay up to date with all of NASA's missions to explore the solar system and beyond at nasa.gov. I'm Preston Dykes from NASA's Jet Propulsion Laboratory, and that's what's up for this month.
Looking to power surface exploration on the moon, new imagery from the surface of Mars, and our newest flight directives. A few of the stories to tell you about this week at NASA. NASA and the U.S. Department of Energy have selected 3 design concept proposals for efficient surface power system design that could be ready to launch on a demo mission to the moon by the end of the decade. Fission systems are relatively small, lightweight, and can enable continuous power regardless of location, available sunlight, or other environmental conditions. This technology would benefit future exploration under our Artemis program. For more space technology, visit nasa.gov/spacetech. NASA's Curiosity Mars rover has spent the past year traveling through a transition zone on the red planet, but could also provide evidence that a major shift occurred in the planet's climate billions of years ago, which led to the dry conditions that we see today. Curiosity will celebrate its 10th year on Mars August 5th. For more information about Curiosity, visit nasa.gov/curiosity. NASA has 7 new flight directives. After completing a comprehensive training program, Heidi Brewer, Ronak Dave, Chris Dobbins, Garrett Henn, Nicole McElroy, Elias Mirmo, and Diana Trujillo will oversee operations of the International Space Station, commercial crew, and Artemis missions to the moon. On June 18th, Howard University in Washington, D.C. hosted a screening of the NASA documentary, The Color of Space. The documentary features thought-provoking conversations between current and former Black astronauts, recounting the influences and inspirations that put them on the path to NASA and what they experienced on their journeys to the agency. Some of the astronauts also gave advice and shared personal stories of hope and resilience to students who have aspirations of following in their footsteps. The 50-minute documentary is available for free to the public on NASA TV, NASA app, NASA social media channels, and the agency's website. Vice President Kamala Harris and Second Gentleman Douglas Emhoff recently hosted an event at the Naval Observatory that included NASA STEM education activities for military families and local students and their families. The event also featured a special screening of the Disney Pixar film, Lightyear. Several current NASA astronauts attended the event, including Tom Marsh Associate Administrator for Education, Leah Melvin, was also there. Our Office of STEM Engagement seeks to attract and engage a diverse group of students to STEM fields, to contribute to NASA's work, and to build a diverse
Humanity has always been interested in exploration. We really want to go to the moon. We have got to figure out a way to keep our propellants cold long enough. My name is Monica Guzik, and I have the coolest job at NASA because I work with cryogenics. Cryogenics is the study of things at very low temperatures. We've got electrical connectors we can plug into. So we want to store things like oxygen or hydrogen, but if you store them as gas, the only way to get a whole bunch of molecules in there is to raise the pressure really high. So instead, if we make them really, really cold, they turn into a liquid, so they're way more efficient to store. So this is going to be a liquid oxygen test. I always knew I wanted to be an engineer since I was a little girl. My dad was an engineer, and I just thought engineering was so cool. We were going to put insulation over this. Ended up getting a summer internship here at NASA Gun Research Center in Cleveland, and just really sort of fell in love with NASA. Cleveland is the rock and roll capital of the world. I really enjoy rock and roll music, so I try to go to a lot of concerts. When we improve cryogenic technologies for space applications, it always has a trickle-down effect to Earth. Now we're rolling into the Artemis generation, and we're still doing that.
Hi, I'm Jacob Bleacher. I'm a geologist. That means I study rocks and dirt on the Earth and planets. This is Ask NASA. I'm here to answer your questions. What is unique about the surface of the moon? Well, the moon is quite unique from the Earth. It has no atmosphere. There's no air to breathe. What that means is that the processes that have occurred on the moon are all preserved there in the rocks. For instance, if you look at the moon from the Earth, you may see circles. Those circles are impact craters. So let me show you. Except, making craters is really dirty business. I need my crater-making poncho. Now we're ready. Let's pretend this is the surface of the moon. It looks a lot like this. That's one crater, but the surface of the moon has many more.
Oh, that was a good one.
On the moon, these craters have formed over time, and as you saw, material from each crater buries the previous ones, making this very rough terrain. In that terrain, at the pole, there are some craters that we believe have water ice trapped there, and they never see the sunlight. That's good for science, and could also be a resource that helps our astronauts survive. Why study moon rocks? Well, besides the fact that rocks are awesome, each rock is kind of like a person. It has its own fingerprint. We talked about impact craters. That's recorded in the rocks. Whether or not ice or water has been near there, that's recorded in the rocks. It tells us the history of the moon. What tools will astronauts use to explore the moon? Well, hopefully we'll have plenty of tools for them. For instance, something like this. This is a hammer like you would use here on Earth. It's a geologist's best friend. It helps us to break up rocks and select samples. We could also use things like rakes and shovels to help us find the right kind of material to bring home. Eventually, we could be using tools more like this. This tool is an X-ray fluorescence spectrometer, or XRF. An XRF basically shoots X-rays at a rock and then detects what comes back. And as I talked about before, rocks have unique fingerprints. This helps us to determine what that fingerprint is. Our astronauts will also use rovers, like this model that you can see right here. These vehicles are designed so that they can help us move around on the surface. Well, this tool is 3D printed, but this is just a model of an XRF. But right now, we're actually testing 3D printers in space on the International Space Station. It'd be really helpful if we can use 3D printers to design the tools that we need. How are we preparing astronauts to investigate the moon's surface? Well, we have to practice here on Earth. The way we do that is we talk to them in laboratory and classrooms, and we also take them out into the field, places like Hawaii, or Iceland, or Arizona. Places where there are similarities to what they might experience on the lunar surface. We're really excited to send humans to the moon with the Artemis program. First woman and the next man will be going back there by 2024. Together, they'll be able to explore the surface of the moon. And right now, our plan is to send crew to the surface of the moon once per year and bring more supplies to the surface so that we can explore more and more of the South Pole region. That is a great question. The first thing that's going to be very different is that during Apollo, the sun was overhead. But at the South Pole, the sun is always going to be right on the horizon. That means we'll have really long shadows in areas that are very dark. It's going to be very different. We really are exploring a brand new terrain no one has ever been. The studies we'll be trying to do are looking at and understanding perhaps the water cycle. We really want to understand the processes that lead to that water being preserved for getting at the inside of the crater. Every time a crater forms, there's an explosion that moves rock up and out from inside of the moon. So deep inside, the bigger the crater, the deeper the rocks. Well, in fact, we are aiming for farther out. Eventually, we want to get to Mars. But first, we're going to go to the moon and learn some really important answers to questions that will help us survive the trip out to Mars. Because I guarantee you, I'm going to have a lot of questions for them when they get back.
Do you have a question for NASA? Send your questions to our experts using hashtag AskNASA.
Station, this is Houston. Are you ready for the event?
Station is ready for the event.
KNBC TV, this is Mission Control Houston. Please call station for a voice check.
Station, this is Naomi Lee with KNBC TV. How do you hear me?
Hi, Naomi. I have you loud and clear. How me?
Loud and clear. Good morning, Dr. Watkins from Los Angeles.
Good morning, and welcome Los Angeles.
It was an honor to speak with you this morning. First of all, can you tell us a little bit about your mission and the work that you're doing on the ISS?
Yeah, absolutely. So we are up here. We first arrived on station as part of the NASA SpaceX Crew 4 mission. So we came up here on a SpaceX Crew Dragon, and we are now part of Expedition 67 on the International Space Station. And up here, we are doing lots of science, conducting lots of different kinds of scientific experiments, including physical science, biology, technology demonstrations. We're doing Earth and space science, which is near and dear to my heart, and then human research as well, where we become the test subjects ourselves. We also perform quite a bit of maintenance on board the station, helping to continue the life and the legacy of the ISS out to 2030 at least. So that's a big part of our mission as well. And then to involve our international counterparts as well. So we have one of my crewmates, Samantha Cristoforetti, is an ESA astronaut, European Space Agency from Italy, as well as our Russian colleagues. So we have multiple missions coming together to accomplish the most science that we can.
Well, you mentioned that subject that's near and dear to your heart. You have a doctorate in geology from UCLA. How are you applying your expertise to your work in space?
Yeah, for me as a geologist, and particularly as a planetary geologist who spent, as you mentioned, my graduate work and research thereafter thinking about the geology of other planets. Being up here on ISS gives us such a unique vantage point that it is really easy to make comparisons to the way that we're able to see planetary surfaces, in addition to kind of how we're able to see the surface of the Earth from the ISS. So to be able to make that comparison, especially for places that on the ground that I have visited, I've done field work in, to be able to see that from kind of a planetary perspective, if you will, has been really, really neat. Arrived. The most challenging aspect of being up here is just the kind of adaptation process where your brain is learning to think and move in 3 dimensions. So learning to use the walls and the ceiling to climb on, and then also to just reorient yourself to be able to utilize the full volume of the International Space Station. Certainly took some getting used to. I as soon as I felt up to it, I did one pretty immediately. Still working on it, but definitely a extended period of time. We certainly miss our family and friends and everyone that we know, lots of different types of food. And it's true, but it actually did a pretty good job. It was a pretty good substitute. We had some supplies that were flown up on the Boeing Starliner, the CST-100 vehicle that came up on the OFT-2 mission not too long ago. And it brought with it lots of science and supplies, and luckily for us, some treats as well. So that's what enabled us to have that awesome pizza party.
All right. Well, you are the first Black woman to serve on a long-duration mission on the ISS. What message do you want to give to other women hoping to follow in your footsteps?
Who helped me along the way. So I think I would say to anybody who is interested in whatever it is that you're interested in pursuing, to pursue that relentlessly, and then to find people that will help guide you along the way.
And going off of that, a lot was said, when you launched to the ISS about your history-making status. Do you think we're not too far off from where those types of headlines, I guess, won't be such a thing and won't be such an unusual or milestone-making topic?
So sorry, can you repeat the last part of the question?
I'm sorry about that. What I was wanting to know is that, you made history with your trip to the ISS. Do you think we are, I guess, closer to having more women and more women of color, so where the headlines aren't as prevalent, is what I'm trying to ask? It's not such a big thing. It's not like we're
yeah, absolutely. Yeah, no, absolutely. I think the thing about, as we celebrate these firsts, and we're hoping to celebrate more firsts as we look towards the moon and eventually to Mars with the Artemis program, NASA's Artemis program as well. But I think ultimately the goal is to not have any more firsts, right? The intent overall is to get to a point where we have so much diversity and representation that there are no longer places for.
Thank you. Any messages you want to send to anyone back home?
Yeah, absolutely. Shout out to City of Los Angeles, to UCLA, everyone at UCLA, go Bruins. Also at Caltech, go Beavers, and my colleagues down at JPL as well. Hey, everybody.
Before we let you go, we want to wish you a happy belated birthday. How was your party?
Oh, thank you so much. Yes, it was one to remember, that's for sure. Certainly unlike any other birthday I've had. It definitely gives you some perspective, kind of doing another lap around the sun while you're doing laps around the earth. It was pretty special.
Well, thank you, Dr. Watkins. It has been a pleasure talking to you. We hope to hear all about your mission when you're back on Earth.
Absolutely. I look forward to it. Thanks for your time.
Thank you.
Station, this is Houston ACR. Thank you. That concludes our event.
Thank you to all participants from KNBC TV. Station, we are now resuming operational audio communications.
I think every person, and I think every one of us started with NASA with that dream.
Okay, to start, first tell us a little bit about how you got here. And then if you could share with us who Mark is.
Okay. Well, I've been out here 12 years. I'm a research laboratory mechanic. They hired me on actually as general labor and said if I did really well, I had a chance to get into the NASA apprentice program. So I did really well, and I got into the program. They sent me to school, and then on-the-job training hours to learn the skills that I needed for here. And I guess the rest is history.
I'm Cale Yeager.
My name's Erin Reed. I'm a test engineer here at SEC.
I'm Nicole Smith. I'm the project manager for Orion testing here at NASA's Plumberton Station. For the better part of the last 12 years, I've been working on some legislative fellow on the Hill for the senior senator from Ohio.
At the end of the 4 years that this apprenticeship is supposed to take, I'll come out as a research laboratory mechanic, have my journeyman's card, and go from there. I've always been a big space nerd, always been a fan of outer space and space travel, and the big question of how do we get here.
I would say my main role out, I run the compressors for the cryo shroud that changes the temperatures in the vacuum chamber. So, and offloads of liquid nitrogen and gaseous nitrogen.
I'm the contamination engineer here. So when I first got here, the facility has generally only been used for large-scale fairing deployments. And so they're not really clean. They're not meant to be in a clean environment. So the vacuum chamber that we've used has always been sort of dirty. And so when I came here, there was a big push to try to figure out how to clean the chamber and how to make the facility clean enough so that when we got a flight vehicle, we wouldn't contaminate the vehicle.
We are standing very high up in the Assembly High Bay at the Space Environments Complex at NASA's Plumberton Station.
The sound, when you take a rocket and you pound it with the sound that makes when it liftoff. So there's a lot of capabilities that this test facility now has. At one time it was just the world's largest vacuum chamber with the world's largest cold wall. So it's much more now.
Trucks a day when we're running the thermal vacuum chamber. You'll have Cale over driving the door. I think he's down there cleaning the floor right now. Everybody is hands-on and does a ton of different stuff. Erin Reed is an example of one of our test conductors, right? So she's going to be that point of contact in between the facility team that's running the vacuum chamber, helping with all the operations. Sometimes you'll see him down here on the crane lifts. And then you have someone like me who's the project manager who makes sure that all these people have all the resources they need. I'll make sure that everybody working on the team knows all the information that they need to know. So we're just trying to tie it all together and keep everyone moving in the same direction.
We are all very diverse. We have to do, we're always joking around, we're always having a good time with one another.
It's a tight-knit group that, I work with, and everybody's pretty accepting here. I do think it's cool for women to see they can break out of maybe a traditional.
Misery loves company. But more than that, we're all working together towards a common goal. So there are lots of disagreements that we have, technical disagreements. We may see things with a different perspective, but we all know that it's because we're trying to create the best solution for what we're trying to do.
Data is our product. We don't make any widgets or anything, so that's our product. So I believe the engineering and the techs here are outstanding. I would put them up against anyone in the world.
So We do a lot of other test articles to prepare. All of the other prior Orion hardware was development. So this one it's huge, and it's going to go around the moon. And we're going to be able to sit there and watch it launch and watch it while it's out on its orbit and see how it's doing and say, yeah, we had a huge hand in that.
You know, I've been here so long that I've seen the transition, and it's so neat to finally see. I spent a lifetime getting it to where it is, and I'm really proud that we're testing flight hardware now. I think it's a credit to the people I work with. I work with some great engineers and great technicians, so very proud of what we've accomplished.
When it's a flight vehicle, you're not just concerned about the data from the test, you're actually concerned about the vehicle itself, because that's the thing that's going to be delivered to space. So that's when it becomes a higher risk.
During the thermal vacuum test, we'll provide a really cold background of space with our cryo wall, and then we'll be able to do different zones of heating to simulate being in a specific part of the orbit where one part of the spacecraft might be in the sun and the other part is in the shade. When we're done with the thermal vacuum test, we'll bring it back out, do some reconfiguration, and then put it back in that chamber, but instead of pumping the air out of it and putting the cold wall in, we'll actually hit it with radio frequency waves to do electromagnetic testing.
When you get into test conditions and you got the chamber pumped down and the cryo shroud's at the temperature it's supposed to be, it can get very boring because everything's running perfectly, but boring is good. And to me, it's exciting. You're part of the crew, you're part of history, really, so I think that's very neat.
Everything we do is schedule driven for the most part, so when schedules delay or schedules, we have to redirect, and that's a challenge in itself. But we keep our crew working very effectively all the time, which is a challenge, and I get excited about those things.
I think the biggest risks are for your optical components. For instance, we have a star tracker on the vehicle. So if you can imagine if a particle of dust or some bit of oil got stuck on the star tracker, and the computer sees it as a star, but it doesn't move no matter how the vehicle moves, that would change how it's going to try to navigate, and it might even mess up some of the algorithms. So there's a lot of those sensitive surfaces that we're concerned about.
If something gets contaminated with the spaceflight hardware, it can be detrimental when they go to launch it. When oil's from your hand, anything can gas off going into space, you're contaminating the test articles coming if you touch it with your fingertips. So we have to be that careful because it is spaceflight hardware.
Outside of work, I have a 4-year-old son and 2 8-month-old sons. We had twins over the furlough, so that was exciting. I'm lucky. My girlfriend is very supportive. She helps out a lot. She makes it easy. Having the twins at home is very tough because she gets run ragged. I get home just in time for bedtime. It's very tough.
So it takes someone that's motivated to try to get it all.
It's huge for me to be a part of it and see the spacecraft come here to Ohio and be tested for 4 months and then see a launch. And I'm really excited about people going back to the moon. So the idea of the first woman stepping foot on the moon and me getting an opportunity to work on this spacecraft here, it's huge. So I'm really excited for that.
Wow. Yeah, it's really coming to
the universe. Because this is going to help us not just get to the moon and not just get to Mars, but then it's going to be the jump-off point to the next place we go. I really feel it's a really awesome thing to be part of. We are taking that next step. We are doing that next.
I'm not even a blip on how this program functions, but it takes all of those people to make something like the Aurora. If that's the part I need to play, I'm happy to be part of it. So it's exciting.
Well, I'm a real go-getter. I like to go, 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 which helps me.
Hey everybody, this is Beck, and I am a maker of music. And like the great Sun Ra said, space is the place.
And I'm Farah. I work at NASA, and I use AI to explore Mars.
And I brought a few friends along who know something about artificial intelligence.
Hi, I'm John.
Hi, I'm Isabel. We are both artists working with NASA using artificial intelligence.
This is Ask NASA.
Yeah, so Beck, you just released a set of new music videos using a lot of NASA imagery, and I grew up loving space, and obviously those images are used by scientists. What inspires you about space, and how you came up with this idea?
Well, the title of the record came from a video game, a really primitive video game from the 80s called Asteroids. When the asteroids were going to kill you, and they were just about to collide with your spaceship, that you would hit this button and it would make you disappear and reappear somewhere else in the galaxy. And I always wondered what that button was called, and I looked it up one day, and it was called hyperspace. So I sort of it got my mind thinking into music and song ideas. Because I think in some way, I think music has sort of a hyperspace button. You know, it's something that we existing in the songs.
Artificial intelligence is the...
Beck was already creating a sonic environment that went to like the edges of our understanding and the way that we see, and that's something that we're most excited about working with AI with. But it expands in a 512 dimensional space. The process begins with the AI training on the images. So if we showed it just a few hundred, many images as we could show it, I think in the end it looked at over 25 million images. Sometimes that was multiple times looking at the same images to try and understand these images.
We get started in the process of exploration, right? And so when we first went to Mars, or when we sent Cassini to Saturn, we had some thoughts about what we might find based on that imagery, and that's what allows us to really focus down on the type of science we're going to do.
I worked a lot on the database creation, and I feel almost like I could draw a picture of the galaxy now, just from going, like anyone can do, just by working with the NASA websites and going through the archives. Like the AI was then able to take that and recognize colors that were happening a lot, recognize shapes that were happening a lot. I remember when it first showed us what it thought Saturn looked like, I was blown away.
Yeah, and even then, seeing these images and getting all the info, it is overwhelming. We're talking about other worlds we'll never get to experience in our lifetimes. This is the closest we'll come to. This project is so interesting because it really came out of the theme of the record. I would have loved the idea of taking sounds from these missions in space and putting them into the music itself.
The coolest thing that we have coming up, which we can point you to when it comes out, is that Perseverance actually has 2 microphones on board. It's the first time we'll have real audio from Mars. So we'll have audio as we're landing on the planet, so that we're doing entry, descent, and landing. And then we'll have audio when we're driving, so you'll be able to actually hear that laser zap on another planet, which is kind of something that's kind of hard to even wrap your mind around.
And that hasn't been recorded before?
No, not with a microphone, not this way. We've never had a microphone on board.
Okay, well, send those audio files my way when you get them.
Absolutely. So on Perseverance, we actually have an extra computer, and so that extra computer allows us to make the rover smarter. And we actually...
One of the easiest ones, because it's where we have the most high-resolution imagery. It's been so well captured from so many different points of view.
We've seen the soil on terrestrial level, and then we also have imaging of Mars from above, and looking through this data set of massive data set of incredible images. Once we trained the AI on that, it was able to kind of produce such vivid, strange imagery, because Mars itself, I think, is so much more complex and so much more deep and varied than we imagined it is.
Okay, so one more cool feature about the Perseverance rover is that it can also act as a scientist. The rover can look at the environment around it, look at all the rocks, and say, hey, this rock over there looks really cool. Let me image it, use my laser to zap it, and figure out what's under that surface, send all of that data back to the scientists. So it allows us to essentially have scientists on Mars making decisions without having humans in the loop here on the ground.
I think, to me, the idea of space is a bit overwhelming and awe-inspiring. Just the idea of listening to a piece of music and we go somewhere else. Our lives change. You know, it's a mirror to this other idea of space and space exploration. And letting the imagery of these other worlds, these unknown places with this music, I think has been really satisfying to me. I feel really fortunate to have you all open your doors to me and my music, and for us to go somewhere with it that was unexpected, even for me.
Let
me get my video up.
Sorry, guys.
We'll get it. We'll get there.
We'll get there.
This is Ask NASA. I mean, that would be the show tune way. With all kinds of guitars, trap music, it's the Moog. And this is responsible for most of the music of the 80s. There's a couple of pedals that I used, little bits and bobs.
From the solar winds to the mystical auroras, science is a way of knowing. Lluvia studies charged rockets into the auroras. And Amber Versteinen is an undergraduate student majoring in atmospheric science. Amber's internship at NASA helped put her on the path to a career in science. Dr. Weil, can you help us learn more about the nature of science?
It's about understanding the natural world around us. Science is about finding new information, which inherently comes with being wrong a lot of the time. By definition, you're exploring space and questions that nobody has really thought through before.
Dr. Samra, how do these questions drive the study of science?
We'll ask questions. We'll try and figure out what experiment might help us answer this question. We go for it. Usually we don't figure out no idea how the aurora was created, but people would notice that when they had a compass and there was aurora going on, funny things would happen. So they knew it had something to do with the magnetic field.
Scientists use different methods and tools to gather a variety of mathematical data. Data may include images, numbers, patterns, shapes, and calculations that help model and describe the world around us.
So think of images just with like a camera, that's a remote data set. You can do it in optical light, but like what we can see with our eye, just like with a regular camera. But we can also look at the sun in other wavelengths, other types of light, like X-ray light, ultraviolet light, infrared light. And so those are other types of information about the sun. The other type of information that we can get is called in situ, and that means measuring directly where you are.
In the case of aurora, we're trying to launch and go over the aurora in what we call the apogee, which is the highest point from the ground, and make measurements there. By participating on the apogee, we effectively get a snapshot of how the environment, that space plasma environment, looks at that particular time, at that particular altitude. It's surprising how much science is in just a couple of minutes of these measurements.
When we look at data for a long enough period of time, we can really make sure we're not just answering one little question about the sun, but that we're really pulling all of the information together and making sure the big picture still makes sense of how we think the sun works. When good science is being done, it leaves room for us to change our mind, to realize we were wrong about how something was working as we get new information, and we have to refine our ideas about how the natural world
Scientists do their best to understand observations with the knowledge and tools they have, but sometimes scientific explanations change.
So I think of science as basically a puzzle. We have tiny pieces of a big puzzle. Every time we have a new piece that actually connects, our image changes.
We do our best to describe what we see and what we're observing, and then we figure out which parts still aren't making sense. Sometimes the model will make sense and explain all of the observations that we have today, and then tomorrow the sun will do something totally different and we'll have new observations. It's not even necessarily that the model was wrong, it's just that the model was incomplete.
It's important for all of us to understand the nature of science because we can all be scientists, asking questions and gathering data. Amber, you've had a chance to collect data during your internship at NASA. What were you studying?
While I was in high school, my first project was studying ozone and how it affected plants by working on an ozone garden that was at the Virginia Living Museum. An ozone garden is a garden that consists of like different types of plants, some that react to ozone and some that don't. So some of the tools we used was a meter stick to measure the heights of the plants. We used a rain gauge to measure how much rain all of the plants were getting. We used a thermometer to measure the air temperature that the plants were growing in, and we used a psychrometer to measure the relative humidity of the garden each day. The ozone garden research was really important because it shows how different plants grow more efficiently in different climates and how ozone has such a big effect on plant growth. This is really important to understand with our changing climate.
I try to force any pieces that don't fit.
It's important when we do science to do our best to overcome our biases. Everybody has biases. It's important to be ready to be proved wrong.
Science is a human endeavor, and our understanding of science is constantly changing. Men and women from all cultures and backgrounds.
All the tools you have to collect evidence. Even do a citizen science project. You could even do an internship, maybe even at NASA.
So what are you waiting for? Science is an amazing way to use math to help uncover grand mysteries in the natural and material world. Special thanks to Dr. Nicolene Weil and Dr. Marilia Samra for helping us understand more about the nature of science.
Into work physically very often. It has been a year of remote working. I stopped by my office today because I wanted to get some things done, and I hadn't checked my mailbox in 8 months. And so I just walked into a giant stack of mail because clearly all of you guys have still been writing your letters. So I have decided I'm putting off my work for today.
Don't have any washing machines, no dishwashers, no laundry, none of that.
So my first piece of mail comes from North Bend, Washington, and it says, "Attention aliens. Do not fear, do not attack. I do come in peace. Doa Mijik." Thank you, Doa.
This is one of my favorites. It's from Elena. It says, "Dear Mr. Morgan."
I'm in the 3rd grade. Space interests me with rocket ships, planets, and science. How big can asteroids get? We actually just had a recent mission called Osiris, where we landed a spacecraft onto a near-Earth asteroid called Bennu. And Bennu is not the biggest asteroid in our solar system. Asteroids can be really, really large or more on the smaller side like Bennu.
Moving on to the questions. What made you become an astronaut? Have you ever seen an alien? When you use the bathroom, when you flush the toilet, where does it lead?
Here is a future poet, future novelist, artist who has written a poem. Jump off my bed and into space, stars and planets all over the place. There's the moon, there's the sun, space is so much fun. But gravity pulls me back to the station. I wish this wasn't my imagination. It is good that gravity pulls us back to something, especially the space station. Don't want to go floating off into space anywhere.
I'm going to go ahead and pass this to our chief astronaut.
First question here is from Devin Yarkles. He wants to know, that's what spacesuits do. They protect us. When we go up and down
big. The Russian on the Soyuz, the Russian spacesuit called Sokol, it is a really neat space station. One is the American Extravehicular Mobility Unit, or the EMU. You can see it right here. It's white. We wear different color stripes depending on who's the EV1 and EV2, so we can tell each other apart because we all look very similar in the spacesuits. And then the Russians have an Orlan.
They really are, and I think this astronaut is on an asteroid or maybe the moon. Either way, that's pretty cool. Anyone who wrote one of these fan mail letters from elementary school, and they could be the one walking on the moon or walking on an asteroid someday.
How long does it take to go back home? How long does the food last? What does it feel like when you're floating? Bye. Hope you enjoyed what you read. Sincerely, Elena.
I mean, did this even have postage? Or did the post office just bring it?
If you have a moment and could share your advice as an astronaut and successful woman of science to a young girl who cannot stop talking about all the experiments she wants to conduct when she lands on Mars, we would be forever grateful. Well, Eliana, I would say keep up that excitement, and the most important thing is to keep asking questions. Keep that curiosity alive, to explore, to study, to learn about science, technology, engineering, math. Follow what it is that you're passionate about. Your dreams can come true. I know that for a fact.
Greeting, Astronaut X. I'm a high school physics and astronomy teacher at Ridgeline High School. I would like to start a wall of astronaut photographs adjacent to the display of my space patch collection, and she has a photo of all the patches that she has on the wall. Well, Emma, as a super teacher, you're continuing to inspire the younger generation. I'd like to thank you for your work. Thank you for the hard task that you have. Woo-hoo! To teachers.
Dear astronaut Dr. Kim, my name is Gracie. I'm in the 3rd grade. I thought it was funny how you got called in the grocery. If I got called there, I would go crazy. We went crazy too. I was in the grocery store with my wife when I got the call from the selection committee that I was selected as an astronaut, and it was a very memorable time.
Hi, my name is Carolyn. I go to Charlotte Preparatory School in Charlotte, North Carolina. Did you know that my middle name is McLean? Stop. That
dog. You're more amazing than a dogacorn. That is quite a compliment, Jory. Thank you so much. This is beautiful.
Look at this one. This is so colorful and pretty. This one is even on both sides. Look, it has all the planets. There's Pluto there. Oh, yeah. At the moon heart, there's Pluto at the bottom.
Got some real artists out there. This is Lucas, 3rd grade. Did a great job of depicting our entire solar system. I love it because Pluto is still there.
Is Pluto a planet, or did Pluto explode? As far as I know, Pluto has not exploded.
I think that's it.
Thank you so much for the fan mail. It means a lot to us.
Thank you, everyone, for your letters.
I am so thankful that everybody took the time to write me on this Thanksgiving, and it's going to take me forever to go through all of these, and I love it. Thank you.
Thanks for the letters. Thanks for all the questions. Keep them coming. We love it. We love it.
It is so nice to see all of this fan mail and to know that everybody is thinking about us here at NASA, especially during the holidays.
From the entire astronaut corps, happy Thanksgiving.
Happy Thanksgiving.
Happy Thanksgiving, everybody.
Have a happy holiday and happy Thanksgiving.
Happy Thanksgiving.
Happy Thanksgiving. Thanks for the mail. Keep it coming.
Happy Thanksgiving from Johnson Space Center, everybody.
By the way, we just got to 1 million followers on Twitter. Couldn't do it without you. Tweet us your fan mail questions. Hashtag AskNASA. Hashtag NASA. Hashtag Dragon. Hashtag Spacewalk. Hashtag Artemis. Hashtag Starliner. Hashtag the universe.
Today's telescopes study the sky across the electromagnetic observing campaign known as GOODS, which reaches across the spectrum and deep back into cosmic time.
And in space. Now to do this, we've set up a similar collaboration between ESOcast, the Hubblecast, the Spitzer Space Telescope's Hidden Universe, and the Chandra X-ray Observatory's Beautiful Universe.
I'm Megan Watsky, for the Beautiful Universe, from the
This project so important. The longer a telescope spends looking at a target, the more sensitive. These are the key ideas behind the Great Observatory's Origins Deep Survey, or GOODS for short.
Very Large Telescope, the NASA ESA Hubble Space Telescope, The Spitzer Space Telescope, the Chandra X-ray Observatory, and evolution of galaxies across cosmic time, and mapping the history of the expansion of the universe.
Despite the fact that the whole field is actually only a tiny speck of sky, about the size of a grain of sand held at arm's length.
Now, with goods, many different observatories have brought their powers to bear on two larger targets, one centered on the original Hubble, the size of the full moon.
Of the history of galaxies.
At ESO's Very Large Telescope on Será, the 8.2-meter diameter giants were used for a total of almost 100 nights of dedicated observations. The telescopes made images of the region both in chance to observe through the Earth's atmosphere.
The NASA ESA Hubble Space Telescope observed the goods regions at optical and near-infrared wavelengths in order to detect distant star-forming galaxies, among other things. Now, Hubble spent a total of 5 days observing the fields, spread over 5 repeat visits.
It wasn't just Hubble making space-based observations for us. NASA's Spitzer Space Telescope imaged the goods regions in near and mid-infrared light for 5 days, at wavelengths up to 30 times longer than the Hubble observations. These longer wavelengths are important for revealing distant galaxies whose light may be obscured by cosmic dust or stretched by the expansion of the universe, making them invisible to Hubble. These also tell astronomers about their age and their total mass of stars, complementary information to the data from Hubble. Now, let's move from the infrared to much shorter wavelengths.
Also in orbit, the Chandra X-ray Observatory had already observed the goods field in many long observations taken over the course of a year. The Chandra images of interstellar gases falling into the black holes.
These multi-wavelength observations identified tens of thousands of galaxies. To get a full understanding of the history and development of galaxies over the vast stretch of the universe's history, we need to be able to pin down their distances more precisely to fix them in cosmic time. As these galaxies are so far away, the light waves we see from them today started their journey up to about 13 billion years ago. And because the universe has been expanding since the Big Bang, back then, the universe was less than 1/7 of its current size.
During the billions of years of the light's journey, its wavelength has been stretched as the fabric of space has expanded. This effect is known as redshift because, for example, light that was originally blue or ultraviolet in color is shifted to longer and redder wavelengths.
Back on the ground, astronomers used spectrographs on ESO's Very Large Telescope fields. Now with this knowledge, we can place the galaxies at their distances along a vast cone of space, stretching out from our own vantage point like a searchlight beam into the cosmos. We can take an amazing journey through kind of a tunnel towards the edge of the universe. In some places, the galaxies cluster together, forming structures which are up to tens of millions of light years in scale.
Thanks to goods and other surveys of the same region, these areas of the sky are uniquely well studied with high-resolution, deep observations across a wide wavelength range. Plus, there's more to come. For example, the Atacama Pathfinder Experiment Telescope, or APEX, has spent a total of 300 hours, nearly 2 full weeks, imaging the region at sub-millimeter wavelengths from its high site on the 5,000-meter altitude plateau of Chajnantor in the Chilean Andes.
Observations at these wavelengths are ideal for finding the redshifted light of distant, dusty galaxies in the very early universe. Because of the longer wavelength of its sub-millimeter light, the apex image is not as sharp as the visible light and infrared images. However, thanks to the deep Spitzer images, as well as images made at radio wavelengths, we can match up and identify the years. ALMA, the Atacama Large Millimeter Submillimeter Array, currently under construction on the same plateau. ALMA will revolutionize our understanding of the early universe by revealing many more distant, dust-obscured galaxies that cannot be seen at all by visible light and infrared telescopes. Based on these data, with even more in the pipeline. And on top of that, the observations of the goods fields will continue in the future. These patches of the sky will be prime targets for the next generation of telescopes, both on the ground and in space. And astronomers around the world will use these data to learn new things about the universe for many years to come. Saying goodbye to our friends at the other observatories, this is Dr. J, signing off for the ESOcast and the Hubblecast.
This is Dr. Robert Bird, signing off from Hidden Universe, Spitzer Science Center.
Which I'm sure will surprise us beyond our wildest imagination.
Facility on the eastern shore of Virginia. We're here because NASA is using airplanes to study hurricanes. The mission is called HS3, which stands for the Hurricane and Severe Storm Sentinel. What's a severe storm sentinel? It's actually a remotely controlled airplane called the Global Hawk Unmanned Aerial Vehicle, or UAV. Pilots fly the plane from a cockpit on the ground. NASA is using these Global Hawks to study hurricanes in the Atlantic Ocean by flying over and around them. The Global Hawk can fly for very long periods of time at very high altitudes. It can fly almost twice as high as a commercial jet, and it can fly for over 24 hours without stopping. That's why scientists are using the Global Hawk for the HS3 mission, so they can continuously study storms as they develop. Forecasters have a pretty good idea of where these storms go, but what they want to know is, will they grow? We spoke with NASA mission scientists about how the Global Hawk will help improve their understanding of hurricane formation and growth, and why it's so important for us to learn more about hurricanes.
The Hurricane and Severe Storm Sentinel has a goal to try to better understand the processes that control the intensity of storms. The ability to predict the intensity is very important because it impacts people in the coastal zones who, if they're anticipating, say, a tropical storm, a Category 1 storm, and they end up getting a Category 3 storm, it makes a big difference in terms of their ability to prepare and deal with the storm consequences.
And this is really important because a category of a hurricane is the intensity of the winds associated with a hurricane. So a Category 5 hurricane is much more destructive than a Category 1. So being able to predict the difference between just a tropical storm, a Category 1, up to a Category 5 is really crucial.
24 hours, and being able to monitor a storm for that long period of time and getting constant data, we can actually catch changes in the storm.
We will use two Global Hawks. One Global Hawk flies over vast areas around the hurricane. It measures the environment that a hurricane is embedded in. And then the second Global Hawk, instead of sampling the vast area, it goes right.
Flown by NASA were originally built for the military and used for flight testing at Edwards Air Force Base in California. When the Air Force was done testing these models, they were transferred to NASA, which turned the planes into airborne laboratories to study the Earth. NASA flew its first science mission with the Global Hawk in 2010.
The Global Hawks are really a new aircraft for doing hurricane studies. Manned aircraft typically fly for, say, 8 to 10 hours when they do a research flight. Of that 8 to 10 hours, you may have 4 hours or more just getting to and from the storm, so that in a typical flight, you only get 4 to 6 hours actually sampling within the storm. With the Global Hawk, we can get 3 times, sometimes even 4 times as much as you can get with manned aircraft.
Now this plane can fly to 65,000 feet. It can fly 13 miles up. It can also fly for nearly 30 hours. So this plane can take us if we have.
Because the global hawk can fly so high for so long, scientists can study larger areas of the Earth for longer periods of time, in places where planes with pilots on board may not be able to reach. We spoke with pilot Phil Hall about the global hawk and what it's like to fly the plane without actually being inside it.
So the two global hawks that we're flying for HS3, Air Vehicle 6 and Air Vehicle 1, from a pilot perspective, it's a very different aircraft. We basically like a trailer. It's been specially designed for global hawk. It's full of computer systems that can talk to the aircraft. So we can connect to the internet, and all these satellite products of lightning, the storm, the satellite images, we're able to download that almost real time and use that to actually navigate the storm. For the first part of the mission, we actually fly the aircraft from Wallace. And once we get about 2 or 3 hours into our flight, we actually transfer control of the airplane back to Edwards Air Force Base, NASA Dryden Flight Research Center. It's very different from any other kind of aviation operation in that we have pilots on both coasts, and we can actually transfer control of the aircraft during the flight to the other pilots. And when you have these long missions, like 26 or 27 hours, one person can't sit there for the entire flight. So we actually have 3 or 4 shifts of people that come and go to man this aircraft.
Now, pilots know how to fly planes and they can tell the plane where to go, but how does a pilot actually know where to go? You have to have scientific information. Now, scientists sit in a separate trailer. We have computers sitting in front of us. We bring in satellite information. We bring in forecast information. And because weather can change so fast, they can collect that information, interpret it, and then relay it to the pilots and say, well, instead of going over to this point, why don't you go over at this point over here, which is where we think the eye has relocated. So it's a great team between the scientists and the pilots to actually get the most information you can out of a flight.
How can you become involved in our mission? You can follow the plane too, just like the pilots and scientists do, by participating in live chats where you can get live updates on where the plane is flying right from your own classroom.
You can definitely be a part of our mission by actually being able to look at the same screen we're looking at. I'm looking at where the plane is flying with respect to the storm, and you have access to the same data I get to look at. You have access to see the plane's altitude, you can see the wind speeds, you can see the wind direction, and you can chat live with pilots, with forecasters, with mission scientists, and we're looking at the same thing you are, and it's just really exciting to know that you can ask us any question at any time, and we are right there looking at the same thing.
To learn more about our mission, visit nasa.gov/HS3. See you next time on NASA Airborne.
It's the first word from space before history is made. From landing a man on the moon to assembling the International Space Station, NASA's Johnson Space Center serves as the iconic beginning to some of the greatest moments in American history. Moments that are triumphs of engineering and international cooperation. Today, we are leveraging our past successes to create even more daring missions from the moon. Made possible with the Orion and Gateway programs, which are both orchestrated out of Johnson, the desolate moon will serve as NASA's jump-off point as we journey to unlock the secrets of the universe and understand how it all began. Today, we push forward to the moon. Tomorrow, we leap to greater heights and new destinations. There is history to be made. In Mission Control, we eagerly anticipate the first transmissions from unexplored worlds. Giant leaps start here.
celebrates LGBTQ+ Pride Month.
That was our first view of ourselves. We really are the blue planet. We're hanging out here in the middle of nowhere. In fact, Apollo imagery was part of the justification for putting together a satellite that would look at the Earth.
That satellite was the first Landsat. The Landsat mission now holds the title for the longest continuous space-based record of Earth's land in existence. At least one Landsat satellite has been orbiting the Earth since 1972. That's nearly 50 years of steadfast observation. The program was born in the midst of several historical flashpoints during a time when the world was changing quickly.
Well, it really was a perfect storm. We had a lot of technology coming out of World War II with air-flown sensors. We also had an awareness of the environment between Rachel Carson, even Stuart Udall wrote a book called The Quiet Crisis. Those two things together, the space race, all of those came together.
But the Landsat story doesn't actually start with NASA. It starts with the United States Geological Survey.
There were a couple of really interesting players. The primary one is William T. Pecora, and he was director of the U.S. Geological Survey. His boss was Stuart Udall. He tried floating it around, and it didn't quite make it. Department of Defense, the CIA, NASA, which was just beginning at that point, they all said, nah, this isn't the right time. So in 1966, Pecora and Udall announced that, okay, fine, Department of Interior will launch. And so that caused a big kerfuffle, and the bottom line was that NASA was forced to step up and say, yeah, okay, we'll do it.
But let's pause for a second. Obviously, there was a big push to make an Earth-observing satellite. But what exactly did it need to do? Landsat's entire job is to collect light, visible light like this, and non-visible light like this. After Landsat captures the light it sees, it can make two kinds of pictures, true color images and false color images. Did you know your eyes can only detect red, green, and blue? It sounds crazy, but it's true. In fact, if you took a magnifying glass to the screen you're probably looking at right now, you'd see a jumble of red, green, and blue dots. Mix those colors together with different intensities, and your brain interprets all the colors of the rainbow. True color images are made by combining red, blue, and green light. But what's even more amazing, Landsat also captures infrared light beyond what we can see. That light can reveal some incredible things when you look at a false color image, like the difference between types of plants, how healthy those plants are, healthy coral reefs and even dead coral reefs, fire tracking, ocean pollution. The possibilities are nearly endless. In fact, I bet you've probably seen Landsat's influence on pop culture without even knowing it. From Google Earth and works of art, to television and movies. And I should know, before my untimely smooshing by an 85-foot-tall great ape deep into the film, I, your narrator, played Landsat Steve in Kong Skull Island. But I digress. Now, back to our story. NASA and USGS get to work, largely under the direction of lead engineer Virginia Norwood, who was often called the mother of Landsat. Norwood and her team had to design an experimental instrument, the multispectral scanner, that had never Yosemite.
And this was because nobody believes that scanner will work. I think you better give us some assurance.
The true test came when Landsat 1 launched on July 23, 1972. Sadly, William T. Pecora, one of the project's original champions, died just 3 days before Landsat took its place in orbit. But with this launch, the United States and soon the world would step into a new paradigm of Earth observation. Never-before-seen snapshot of land resources in the environment would be key for critical decision-making, decades into the future.
Absolutely. I think as a native Nevadadan, we're aware of the value of water.
This is Matt Bromley. Understanding water scarcity? That's his second nature. He's one of the key players tracking water usage in Nevada and the western United States from space.
Everything from public service commercials telling you to turn off your faucet while you're brushing your teeth, to knowing which days you're allowed to water your lawn based off of whether or not you have an odd or even address. There's years where the water in the river is very, very low, and then there's years where it's really plentiful. And so we're really tied into that variability from year to year.
For a state like Nevada, somewhere between 70 and 80% of the water in the state is used for agriculture.
And so if we can do better with managing irrigation water, agricultural water, it goes a long way with water conservation.
The Landsat program has had its eyes in the sky for almost 50 years. Remember how USGS and NASA teamed up, made a revolutionary satellite, and launched into space? Yeah, that was great. The point is, Landsat's success is due in large part to its forward-thinking tech. Each new generation produces better and better measurements, and you can't conserve what you can't measure.
Yeah, just in agriculture, the ability to look at the consumption of the water, the economic value of Landsat to agriculture alone is several times the cost, or a few times the cost of the entire system, and that's pretty significant.
That's Phil Dabney, self-proclaimed dinosaur. Phil has worked for Landsat since Landsat 7 back in the 90s.
It's always been about the detector. I actually had a bumper sticker that people teased me that only the nerds at NASA would understand, and that was it's the detector sticker. And that's been our limitation.
The detector that Phil is forward to today, when our detectors span infrared frequencies. Landsat 8's thermal sensor is so sensitive, scientists can calculate Earth's temperatures down to a fraction of a degree.
The addition of the thermal was a major addition. And then things came out of that, like evapotranspiration, the ability to estimate how much water the plants are taking out of the ground based on how well they can cool themselves by sweating, essentially. And that's been used a lot in agriculture, water management.
This detector seems to be a pretty big deal. But what does it do? I'm so glad you asked. There are two instruments aboard Landsat 9, so that means there are different detectors. Let's start with OLI. When you're building hardware for spaceflight, you have to keep it in a clean room to protect it from any dust that might block light, and OLI is all about light. Once in orbit, OLI collects sunlight reflected off Earth's surface. The reflected light bounces between a few mirrors to focus the beam on a plane of detectors, all lined up in a row. The light passes through a set of filters to separate out 9 specific wavelength bands in visible and infrared frequencies. Each band provides different pieces of information about the land cover. The second instrument aboard Landsat 9, called TIRS, is a little different. It collects the thermal infrared wavelengths, or temperature signatures, emitted by the Earth. To put it all together, let's go to an engineer. But it's far from being the only tech on board. As the TIRS 2 deputy project manager and systems engineer by trade, she understands firsthand what kinds of life support systems are required to keep these two instruments operational. That power the satellite, cool the instruments down, package the data, send it back to Earth, along with many other duties.
And looking at the data and seeing the smile from the scientists that they're getting the right data, and that by itself is great experience.
Yeah, so I don't know if you noticed, but I get kind of a smile when I start thinking of this Landsat data because it is very unique, it's very special, and it feels good to be a part of work like this.
Yeah, it's being surrounded by people that can do. Failure is not an option, which is a famous NASA phrase. We can do that. We'll make it happen.
It's clear that Landsat tech is delivering on its promise to provide game-changing data. Landsat 9 represents the best of what NASA has to offer. But what happens when your satellite works so well that keeping up with all the information it's sending back to Earth becomes its own monumental challenge?
It was a Friday night even, and it was about 10 p.m., and I got a phone call because I'm on call. Basically, the operator explained that the antenna stopped moving during setting.
This is Mike O'Brien, recounting a call that every ground station engineer dreads. The antenna is down, and you have less than 2 hours to fix it before the satellite needs to make contact with it.
When I drove to site, it was exactly what I thought it was at the time. There was a software problem. And the antenna drove itself into a limit. When it does that, it kills power to the antenna, and it has to be manually manipulated to move out of that area. So I, put the harness on, got into the lift, went up to the axis. You have to open the housing doors, which is no big deal. And then you crank the hand crank, which physically moves the antenna. And it moved it out of that limit area. I had about 12 minutes left before the next pass started.
Let's take a step back to explain why, apart from strapping yourself to a lift 30 feet in the air, this is a stressful situation. A Landsat satellite orbits the Earth every 99 minutes, furiously collecting images of everything below it with each pass. Much like the storage on your phone, in that case, Landsat's internal hard drive fills up and doesn't capture the next round of images. Critical data is lost. Luckily, that is extremely rare, and data is hardly ever lost, especially with a workflow like this.
So every time a Landsat 8 image comes in, I record it on 4 independent different pieces of equipment. That way, if there's a failure, I still have 3 other great copies.
We couldn't really tell the story of data without mentioning Landsat's data renaissance, when a landmark decision changed Earth's. In 2008, Landsat took down its paywall.
I recall having one of our international cooperator meetings. A woman from Russia was there, and she gave a briefing that really highlighted the importance of free data. Basically saying how it was democratizing for countries like hers, where suddenly you had an open source of information where anybody could get access and see what was going on the face of the earth.
Christy Klein manages the entire Landsat data archive, nearly 50 years of it. She knows firsthand how hungry the science community is for Landsat products. The first year's scenes were available for free. Downloads jumped exponentially.
In 2008, we had over 1 million downloads. And today, we typically get 15 to 20 million each year.
Which brings us to our next segment. Look at these. Stunning, right? Wrong. I mean, well, yes, they are gorgeous, but they are also a consistent record of change over time. At its most basic level, it's easy to see how Earth has changed since Landsat 1 launched in 1972. Just look at an early image and then compare it to a current one. Maybe it's changed a lot, maybe a little, but that's about all you can say. Landsat provides more than just pictures, though. From space, it sends back verified scientific data in multiple wavelengths. With Landsat, we can quantify exactly how much each 30-meter by 30-meter pixel has changed. And with the full Landsat archive available at no cost, you can track the complete progression of each pixel throughout the season. And you can do that for millions of pixels at a time. Has a piece of land changed from wetlands to suburban housing? Did forests become farmland? Or, looking closer, have these pixels of forest become stressed due to insect damage? Are those pixels of farm fields suffering from drought? With carefully calibrated Landsat data, it is possible to answer these questions for the whole globe.
It's a slice of human history. It's amazing how well, for this 50 years, we're documenting every change on the planet.
This is Jeff Mason, Landsat 9 project scientist.
My thing has always been history. My academic training is actually in geology, but the thing that I sort of loved about geology was still that kind of long time, right? It's being able to stand in a spot and say that there was an ocean here 50 million years ago, and I can look at the fossils that are indicative of that. The thing that got me into the Landsat record was still that historical perspective. It's not 50 million years, it's 50 years, but still you're seeing before your eyes how the environment of forests change, how agriculture changes, urban expansion, the whole thing, how the planet has changed over 50 years. And not only can you not conserve what you cannot measure, you can't measure the effectiveness of conservation approaches, and you can't measure the change. So we have limited resources, we have environmental pressures, we can do something about them if we have the right information.
When you think of a healthy tropical forest, you think of a cacophony of bird sounds at dawn. and dust. But I don't know if you've been to one of those really deafening tropical forests where you can't really hear yourself think. We didn't really hear that. And so I think one thing that's so powerful about acoustic data is kind of a visceral appreciation for change when you can actually hear the silence.
Dr. Danielle Rappaport is a forest ecologist who uses nature sounds to measure the health of the Amazon rainforest.
Landsat has allowed us to map those changing dynamics and get a really wonderful objective annual time series of how humans have been modifying the Amazon forest.
Landsat helped Danielle and her team target areas of human activity bumping up against the Amazon forest, a region known as the frontier. From there, she used bioacoustics to assess the effects of human activity on wildlife.
Landsat was really the backbone of this study.
Danielle is one of thousands of scientists that has paired Landsat data with an entirely different data set to uncover a more nuanced understanding of the world. In many cases, one set of data can tell you what is happening, while Landsat can tell you why it's happening.
So the case that let's look at is the Middle East, where radiation has led to a depletion of groundwater.
Basically what that means is, the NASA satellite Grace picked up some strange readings in the Middle East that indicated that groundwater had suddenly decreased by an alarming amount. Satellites sound great. After all, teamwork makes the dream work. But how do you make two different data sets from two different satellites sing? Here's the secret. Different data sets are complementary and not in competition. See, Landsat data tells us about local conditions on the land surface: forests, neighborhoods, farms, deserts, farms in deserts. Meanwhile, Grace gives a broad regional view of water levels underground. Using the two together deepens our understanding of the world, letting us see what causes led to which effects. But Grace is not the only partner for Landsat. It nicely complements Landsat's view of the canopy top, which assesses the health of the trees. Not to mention the long data record that lets us track changes over decades. Landsat is also a great complement to other similar land imagers. In fact, our friend Jeff has done a lot of work to harmonize Landsat and Sentinel-2 data. Back to you, Jeff.
Sentinel-2 is very much like Landsat. It's a Landsat-like system that the European Union has fielded since 2015. And so the real key there is putting Landsat and Sentinel together, because increasingly what people are looking for is a daily observation of that kind of resolution. There's been almost an explosion in the number of Earth resources satellites, Earth observation satellites that are out there in the international community. In addition to Sentinel-2, India, Brazil, China, Thailand, they all have their own Earth observation programs. Increasingly, it's about putting all of that together, harmonizing the data, at least using them in time series ways
from 438 miles above for almost 50 years. Like most things worth doing, it hasn't been easy.
I think Landsat program today is healthier than it's been in a very long time. We have two operational satellites now. Landsat 9, which joined the fleet in 2021. And then in the late 2020s, we'll have the Landsat Next system. We don't exactly know what that's going to look like yet, but the planning is in place, and I'm confident it's going to be.
Born during a time of limited technology, Landsat's found planet goes through transformations. Now we're launching Landsat 9, a continuation of that dream. We've enlisted our best and brightest to work on this decades-long mission, and we will for decades to come. 50 more years of Earth data in the future? We'll see you there.
myself.
I am a queer woman.
I am a transgender woman.
I am a lesbian.
I am gay and I'm my authentic self.
I'm the parent of a transgender son. I'm very proud.
I knew I wanted to be in science ever since I was a little kid. I felt that it was really important to be my most authentic self, especially knowing that this was my dream. Queer people can dream big.
Exploration needs to be for everybody. Every person, every kid, if they can see themselves, the astronauts that we send out in space, but also in the teams that make that possible, then we're doing our job. We're doing incredibly difficult and complicated things. We want people that look at things from a different perspective, that can bring us, new ways of solving problems, and diverse and inclusive teams do that.
If someone is in the closet and they see people like me doing our jobs, being effective at our jobs, I think that is the biggest encouragement that I can give them is to show I can be my true self and I can do my job. They accept me 100%. We're all together working on this.
Who I am is enough. And when you resonate that kind of pride within yourself and you exude the love that you have for yourself, before you know it, you got a tribe and you can be that.
I am non-binary. I am gay. I use they, them. There was one instance where I was participating in a candidate lunch, and they actually also used they, them pronouns. And it just felt really nice to see someone else in the room using those pronouns, and I made sure to introduce myself with my pronouns so that they could know you're not the only one here. There's someone here who understands you and really just wants the best for you.
It requires some bravery, but take the leap. Just be honest, be yourself. And if you are yourself and they accept you, then you've found what you need. I've learned how to be confident myself, and I've also sort of established myself here. People know me. I get to work with smart and capable people, and our job is to explore outer space and to uncover the mysteries of the solar system as a daily matter. That's what we do each day.
I feel hopeful for the future because of the education that's out there and employee resource groups that NASA has established. I am my true self, in love with my wife, and if we can be ourselves, our mission here at NASA becomes more effective.
We're all different, and we should all accept each other for our differences, because that's what makes us special.
It's really your happiness.
No matter what your identity is in the community, that there's going to be a place for you, and there's going to be a place for you to not only just be here, but to succeed and to thrive. I am a queer woman, and I am NASA.
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 On the space station, we live in a microgravity environment. Do you think the laws of physics will hold up? Come on, let's go find out.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Jolly good show, Sir Isaac.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
We're going to start with something small, something you might have at home. A little stick of chapstick. We'll go ahead and use our force being in our bungee cord here. We'll put it on our bungee, and we'll pull it back. And you can see how fast it accelerates because there's very little mass. Next, we'll try a little spaceship. A little more massive, and you can feel that because as you move it, you can feel the kind of force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot. Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means the acceleration's faster. And this is the biggest and most massive thing we have. So let's see how the acceleration is affected. Go back the same amount on the force. Here we go. And there you have it. Newton's second law of motion in action. Thanks everybody for exploring a little physics with me today. Now I'm going to send it back to Earth so you can start your experiments. See you again real soon.
Celebrates LGBTQ+ Pride Month.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
the most unusual place. An organization that can challenge conventional wisdom.
We can engineer anything. We can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
X-31 pretty much wrote the book, Quest Vector, along with its sister program, the F-18. An observation of the occultation is one of the more challenging missions that's available.
Right now, we are looking at the dawn of a new era for aviation.
The development of new power in the air has brought about terrific speed. Diving a subsonic airplane at speeds for which they would never climb could be a hazardous business. Knowledgeable men were seriously wondering whether man could ever fly faster than the speed of sound. It remains for the high-speed flight programs to attack these problems with scientific facilities of a new kind.
Rifle and artillery shells have been traveling supersonically for many years. The XS-1 was indeed shaped like a 50 caliber bolt.
Through the sound barrier, the first time ever in level flight.
Blazing through sound barriers and now heat barriers, the Bell X-2 reaches the unheard-of speed of 1,900 miles per hour.
The D-558 was the first American aircraft to use swept-back wings and stall faces. The primary mission of the X-3 was thin wing research. The X-4 with its lap of a horizontal tail. The X-5 could sweep its wings in flight.
Alice achieved a 7-to-1 record over the Big. The United States Air Force played a vital role
Step by step, these different aircraft helped nibble away at the unknown until the frontiers of manned flight had been advanced from speeds of 500 miles an hour to Mach 3.
It was along with Sputnik that we decided to build the X-15. This was a logical step in the research aircraft program. The first hypersonic aircraft.
Designed to investigate the problems of manned flight in a near-space environment. There were many unknowns to be discovered, many problems to be overcome. The hypersonic flow of air would heat the leading edges of the plane to 1,300 degrees Fahrenheit. How could the pilot control the aircraft in air so thin that normal aerodynamic control would be impossible? No engine like this had ever existed before.
50,000 pounds of thrust in a single chamber had to be controlled with the pilot's discretion.
The X-15 pilots flew to study the physiological aspects of high speed and high altitude flight. The data gathered proved to be invaluable to follow on missions beyond the Earth's atmosphere.
They have dramatized the potential of piloted high-performance aircraft in a space environment at a time when much of the world's gaze was turned toward orbital flight.
The aeroplane is an important means of commercial transportation and a decisive weapon of war. The aircraft helped our economy.
Research programs investigate flight at ever greater speeds, time and distance.
Supersonic transport must be durable, and it cannot itself take too much.
The X-43 is a revolutionary new kind of airplane. What we want it to with an air-breathing engine as possible.
To Mach 3.
Though the technology exists for aircraft to fly at speeds faster than the speed of sound, today's aircraft don't.
If an aircraft is flying from New York to Los Angeles, the sonic boom will be heard consistently across the country. We're talking about commercial operations. You're having, 30 in a day.
Would be breaking windows or at least annoying a lot of people.
We can in fact shape the airplane in such a way that we can shape the sonic boom and sound it.
This project is looking to support instrumentation for real-time the real-time map display overlaid with the boom showing where it's in the ground.
Sonic.
It's that pull-out that puts the quiet boom. The end goal is to create a quiet supersonic aircraft. With the F-59 program, we're going to be gathering a series of data from communities around the U.S. relating people's response to the noise to the sonic pumps. We're hoping that the data that we gather with X-59 will convince the regulatory agencies to change the no supersonic overland flight rule.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man's There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
The most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything. We can write the requirements for.
We're going to make your idea work. This particular idea is going to disrupt you.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube go very quick.
The manner in which we fly re-entry pioneered on the X-15.
X-31 pretty much wrote the book on prospecting, along with its sister program, the F-18. And observation of an occultation missions that's significant.
Right now, we are looking at the dawn of a new era for aviation.
Most early inventors thought that flight control could be achieved by a pilot simply shifting his weight back and forth. The Wrights, on the other hand, knew that controlling the plane was the key to successful flight.
Release rates, throttle to optimize. Watch exhaust. Watch nozzle position. Check engine pressure ratio now. And all this time, steer down the runway, first nose wheel steer, then rudder. Lift nose wheel at just the proper speed to fly off in the least ground room.
Today, men coach the high wiggle abilities know better.
Air crew call for ever closer relationships between man and machine.
Until now, former flyers used the force of their muscles, multiplied by years and hours, to adjust wing and tail surfaces.
Your landing gear and flaps are operating hydraulics.
It's about 45.
This kind of control system could make air travel of the future smoother and safer by reducing aircraft vibration caused by turbulent air through automatic response from the computer to the aircraft controller.
We used an F-111 for integrated engine control.
Further mechanization hopes to make more optimum blending of airframe and propulsion system control. A computer-controlled flight system, along with some new control surfaces, allow this modified F-16 to maneuver laterally, change altitude without pointing its nose, and perform other unconventional movements.
Unique system is full authority, digital electronic control, the fastest calculation we can control is 27.
This will be invaluable for military and commercial aircraft in the future.
You can bring it in not for just a survival but a precise normal landing, which is what we did. Absolutely no motion of heavy gas or early modulation of the engine press.
Using neural networks to identify aircraft stability parameters and to optimize control performance during test flights will reduce development and program costs.
A neural network is a computer program comprised of a series of examples, and in our particular case, these examples are previous flight data.
So that saves a great deal of energy, which an aircraft translates to fuel.
This new software allowed the aircraft's flight control computer to minimize drag by automatically determining the best setting for thrust vector nozzles and aerodynamic controls. Thrust vectoring is the ability to direct the aircraft's thrust for directional control rather than relying on conventional control surfaces alone. The intelligent flight control experiment, to be tested in early 1999, seeks to enable aircraft control systems to adapt to unforeseen changes in aircraft operating conditions.
In addition to advanced control research, the FAST system allows for simulating system failure.
Data from NASA's Integrated Resilient Aircraft Controls, or IRAC project, will be used to design and develop aviation systems better enabled to safely fly and land damaged aircraft.
One promising technology that may make it possible to improve both aircraft safety and performance is active stabilization of flutter using advanced flight control systems.
December liner, becoming the first to flight. Heavy experimentations with gliders, like advancements in engine technologies, controls, and aerodynamics, provided a pathway for heavier-than-air crafts, like the Wright brothers flyer. By the 1930s, airships, which have dominated the long-distance flight, were replaced by flying boats and other rudimentary aircraft. By the 1930s and 40s, development of aircraft for war effort, aviation. This stream of innovation led to the start of the Jet Age, which would revolutionize both general and military aviation. Later in 20th century, even more advanced technologies like digital electronics would bring about fly-by-wire, digital engine controls, GPS, and these advancements even changed the way we go about designing aircrafts. This century has been marked by transitioning to large-scale pilotless drones, and for the first time ever, inherently unstable aircrafts, such as highly integrated flying wings, have become a possibility. And with all these advancements in the past 112 years, we're still only scratching the surface. Today we find ourselves at the doorstep of yet another revolutionary advancement in aviation history: electric or hybrid electric aircrafts. NASA is investing in electrified aircraft propulsion research, or EAP, as part of its portfolio to improve fuel efficiency, emissions, and noise levels in commercial transport aircrafts. EAP uses electric motors to drive some or all of the engines on an aircraft. The energy source for the system can be electric, hybrid, or turboelectric. NASA is working across a range of markets, from urban air mobility to subsonic transport. Each market has differences in vehicle size, range, and speeds. Our strategy at NASA is to work with our industry partners to enable technology development, demonstrate these technologies in flight, and transfer the knowledge to the commercial sector for future products and markets. One such emerging market is urban air mobility, developed through NASA's revolutionary vertical lift technology project. Urban air mobility, or UAM, is a conceptual market that would enable passenger-carrying air transportation in and around metropolitan areas. Think of flying goods. These vehicles could use all-electric or hybrid-electric propulsion systems capable of vertical takeoff and landing. The overarching goal of NASA's work in this space is to develop and validate tools, technologies, and concepts to overcome key challenges for vertical lift vehicles. A critical challenge for UAM market growth is public's acceptance that these vehicles can be as safe as commercial air travel or automotive transportation. However, the most immediate impact from NASA's work for the flying public is the reduction in cost through fuel burn improvements and lower airfare prices. To put that in context, let's look at some numbers. The overall global fleet, large commercial aircraft, totaled over 25,000 and is expected to grow to 37,000 aircraft by 2027. Out of the 25,000 aircraft today, nearly 60% of those are narrow-body aircraft, small regional aircraft, both jet and turboprops. Saving just 10% in fuel consumption across this fleet would yield more than 5 billion gallons of fuel savings per year, and is forecast by 2040. We also have to take into account the reduction into CO2 emissions. So how do we get there? The leading concept that NASA is currently investigating for single-aisle turboelectric with IF boundary layer propulsor known as electrically to rear fuselage boundary layer ingesting fan. One of the main sources of drag on an aircraft is a layer of slow-moving air that builds up along the fuselage and wings, no overall improvement in aircraft efficiency. Results indicate that this turboelectric concept has an economic fuel burn reduction of 7%, an emission fuel burn reduction of 12% comparing to other aircraft designs. Turboelectric and fully distributed propulsion system based on superconducting electric machines and power distribution. The fuel benefits of this configuration is very significant, estimated at nearly 70% reduction comparing to conventional aircraft such as Boeing 777. This concept has the best benefits so far studied. However, it requires the most aggressive technology and infrastructure development. And last but not least, NASA is building its first ever all-electric X-plane, X-57 Maximo. This design will demonstrate an effective interaction between wing, the engine propellers, and the flight mission flight path, while simultaneously solving a number of challenging technical issues for electrified propulsion in crew-rated aircraft. While electric motors are more efficient than fuel-burning engines, they produce a significant amount of heat during operation, requiring an integrated thermal management system to be incorporated into the design. This can cause a dramatic increase in weight, thus reducing the benefit gained by electric conversion. One such research, weighing only 2 pounds and completely air-cooled. This system was fully qualified across various facilities at NASA Glenn in 10 short months. And within the next 2 years, our system will be flying on X-57 flights, proving that it is possible to have a lightweight air-cooled solution for aircrafts. In order to qualify the components in this electrified area in aviation, NASA needed to develop capability to test and verify them before in-flight testing. So we converted our hypersonic test facility, Plumberg Station in Sandusky, to NASA Electrified Aircraft Testbed, NEAT, full-scale megawatt powertrains, with an eye towards incorporating component technologies into an overall system. The facility can support single-aisle aircraft geometries with proper cable lengths and electromagnetic interference mitigation. It can supply power for up to 24 megawatts, a thermal management system for up to 2 megawatts, and it even contains an altitude chamber that can simulate up to 120,000 feet. All electric aircraft concepts that we've seen so far rely heavily on advancements of components such as advanced motors, power converters, designs of various high power, density, and high efficient motors for space, aeronautics, medical, and terrestrial applications. All our work has always pushed the boundaries of what's possible, and our newest motor work is no different. NASA Glenn has a small in-house team that is developing a 1.4 megawatt motor with a performance goal of 16 kilowatts per kilogram and efficiency greater than 98%. The motor contains a self-cooled superconducting rotor, which has never been done before, allowing the motor to achieve exceptional specific power and efficiencies without inheriting external cooling weight penalty commonly attributed to superconducting machines. Integrated rotor superconductor, spinning at 6,800 RPM, 4 times higher than the state-of-the-art, and weighing only 80 kilograms. This motor revolutionizes the field of advanced motors and greatly increased number of aircraft concepts that can utilize hybrid architectures. All our electric motor work. This motor was designed to help catalyze advancements in the field of cardiovascular assist devices, such as pacemakers for kids who are born with a single heart ventricle. This motor is tiny in comparison to the ones on aircraft. Currently, our design is being used. All great progress is accompanied with great difficulty. It must be enterprised and overcome with answerable courage. In our efforts, we don't underestimate what might appear to be unconquerable obstacles into traversable pathways and expanding opportunities. I am deeply humbled to have an opportunity to be part of this amazing journey, a journey that will surely.
Hi, I'm Dr. Será. Raccoon in an astronaut suit? Yes! Now we have your attention. We're going to talk about climate change. What do raccoons have to do with climate change? Well, did you know that if the levels of carbon dioxide go to the levels they're predicted by 2050, raccoons are going to start moving further north into colder areas. And while raccoons are cute, they cause a lot of damage when they move into ecosystems where they don't belong. So we're going to talk about 5 things satellites can do to help with climate change. Number 1, they help scientists see the big picture. In a country as large as Canada, we need satellites to keep track of the whole country. We can look at the land, the water, and the atmosphere and see how they interact and change over time, including the impacts of climate change. Number 2, satellites help scientists study clouds and their impact on climate and weather. You may not know it, but those cute, fluffy clouds could actually have a bigger impact on climate change than greenhouse gases. Number 3, measure carbon monoxide concentrations. Satellites help Coastal erosion puts roads, the homes of people who live nearby, and marine ecosystems at risk. Number 5, monitoring the ozone layer and the substances that can damage it. A thinning ozone layer leads to increased UV radiation, which increases our risk of sunburns and skin cancer.
Delivers terabytes of vital information for the process of scientific discovery. Our extensible and expandable communication and navigation infrastructure provides a resilient space framework that can meet the growing requirements of our users. We develop, operate, manage, and engineer pioneering solutions. Transformational technologies in satellite communications are underway. Cognitive systems will enable autonomous satellite networks, and optical communications will increase our ability to send and receive data to the vastness of space. We are developing these and other technologies to advance explorations of Earth, the lunar region, and beyond. Spectrum, the medium that enables communications and navigation. Through coordination, we ensure efficient use of this limited resource. We work with P&T partners to provide space missions accurate position and timing information. The most exciting part of this journey lies ahead, collaborating with commercial industry on major advancements in space communications. Our next generation of visionaries are
of this trapped heat for many years to come. Which unfortunately means next year is probably going to bring a lot of the same kinds of stories that we saw in 2020. But taking a look at all the different ways our planet responds to the variations in movement of heat can help and more severe. With drought and heat waves, we typically see an increase in the availability of dry fuels, which leads to more powerful fires. So when you have multiple years of intense heat, it's not surprising to have significant fire events like we saw in Australia. These fires were so extreme that we saw smoke injected as high as 18 miles above the surface. That's really important because when smoke is injected that high, it can have the same type of effect as a volcano, having these very, very broad impacts across whole hemispheres of the planet. At NASA, we use computer models like the Goddard Earth Observing System to help us the impact will have on you and me. In California, heat waves have increased fire risk, and as a result, we saw a lot of synchronized fire activity. That is, many dangerous wildfires burning at the same time. We have also had a remarkable and active fire season. What we saw was that in forest ecosystems, heat waves can exacerbate fires. And in the Arctic, you also have to factor in permafrost, which is soil that's frozen for long periods of time, and that can make the impact of fires in high latitudes even more complex. When severe fires burn in areas with permafrost, we lose this important insulating organic soil layer, which accelerates thawing, and it's potentially releasing carbon that's been stored in the soil for hundreds and in some cases even thousands of years. And you sometimes sometimes see these zombie fires, which happen when wildfires burn deep into peatlands or smolder in forests under snowfall. If that temperature doesn't get cold enough to extinguish the fire, they can continue to burn over the winter, even long after the visible fire's been extinguished at the surface. So come spring, they reemerge and they continue to burn back on the surface again. Studying what happens in the Arctic is really important because it's warming about 3 times faster than the rest of the planet. And all those aerosols and the carbon that come out of the Arctic don't necessarily stay there. They affect the heating and air pollution in much larger regions of the planet. Another part of the planet affected by heat, of course, is ice. Land ice in the form of ice sheets and glaciers where we've seen significant melt in recent decades, and frozen ocean water, or sea ice. This year, the Arctic sea ice minimum almost reached a new record low. It was second only to 2012's extent, which was an anomalously low year in part due to unusual weather conditions. Sea ice shrinks and grows with the seasons. After reaching an annual minimum extent in September, Arctic sea ice begins to grow again and sea temperatures cool off for the winter. This year, Arctic sea ice had an unusually slow start to the regrowth period. In particular, the Laptev Sea, which is sometimes called a sea ice nursery because much of the Arctic sea ice initially formed there, was too warm for meaningful sea ice growth until much later in the season than usual. Oceans absorb heat from the sun, and our atmosphere prevents this heat from escaping back to space. The movement of this heat is one of the primary drivers of circulation and global weather patterns. We can measure the temperature of the ocean, and what we saw this year was unusually high surface temperatures across the Atlantic. The warm moisture that comes off the ocean acts as fuel to storms. So as this layer of the ocean gets even warmer, we're seeing that storms are becoming more and more intense over time. In fact, 2020 sea surface temperature contributed to an exceptional year in terms of Atlantic hurricanes. We saw 30 named storms, a new record, and 12 of these storms made landfall in the U.S. What's really interesting is that many of these storms intensify really rapidly. Not only are storms intensifying more quickly, but what we're seeing is that they're stalling near coastal regions more often, which is devastating in terms of floods and storm surge. While we're not 100% sure what is causing these storms to stall, it may have to do with climate. Scientists to say any particular fire or any particular event was because of climate change. But we're getting to a point where we're starting to see season after season of record-breaking wildfire, season after season of really intense storms, that it becomes much easier to understand that this is likely the result of long-term climate change. In general, more heat means more energy in the Earth's system. So while 20 anomaly of a year is affected by the shutdown, activities have a powerful impact on our environment. Long-term strategies to curb human-induced climate change would have to focus on implementing cleaner technologies so we can reduce emissions without affecting people's daily lives. So while this is a story about heat, this is also a story about connections. Nothing on our planet happens in a vacuum, and our actions today impact our increases in greenhouse gas emissions, and 2020 being the year that they peaked.
What's up for June? A planetary breakup, prime viewing for a well-known star cluster, and the constellation Lyra. The gathering of 4 naked-eye planets we've been enjoying in the morning sky for the past few months, including several close conjunctions, is beginning to break up. Over the next few months, Saturn, Mars, Jupiter, and Venus will appear increasingly spread out across the morning sky, so much so that Venus and Saturn will make their exits as morning objects for most observers by September. Look for this increasingly spaced-out planetary procession in June, and note that the crescent moon jumps into the lineup on the morning of the 23rd. June is an excellent time to observe one of the best-known globular star clusters, M13, also known as the Hercules cluster. Globular clusters are spherical collections of stars tightly packed together in their centers. M13 itself contains several 100,000 stars. Globular clusters are also extremely old. The stars in M13 are thought to be around 12 billion years old, which is approaching the age of the universe itself. Our home galaxy, the Milky Way, is known to have about 150 globular clusters. They orbit outside the galaxy's disk, traveling tens of thousands of light years above and below its spiral arms and most of its stars. Now, the Hercules cluster is best observed with a telescope, and larger telescopes will allow you to see more of the cluster's stars. But you can also find it with a pair of binoculars, where it'll look like a hazy little spot. Find M13 in the constellation Hercules, which is high in the east in the first couple of hours after dark in June. First look for the bright stars Vega and Arcturus. Then find the 4 stars that comprise the keystone, which is the pattern making up the central part of Hercules. You'll find M13 about a third of the way between the 2 stars on the western or leading side of the keystone. So check out the Great Globular Cluster in Hercules, M13 in June, and find yourself staring at an ancient gathering of stars that soars high above the Milky Way. Finally in June, a quick introduction to one of the smaller constellations that's home to one of the brightest stars. That's the constellation Lyra. It represents a lyre, or harp, played by the musician Orpheus in Greek mythology. In Arab cultures, as well as ancient Egypt and India, Lyra was seen as an eagle. And the Inca of South America saw it as a llama. Find Lyra by looking for Vega, which is the westernmost of the 3 bright stars in the summer triangle. In the northern hemisphere, you'll find it halfway up the eastern sky in the first couple of hours after dark in June. Vega is by far the brightest star in Lyra. It's the 5th brightest star in the sky and the 2nd brightest in the northern hemisphere after Sirius. A pair of binoculars will help you see the other stars in Lyra, which form a sort of parallelogram hanging beneath it. It's sometimes described as looking a bit like a diamond ring, with Vega as the diamond. And that's not the only ring in Lyra. It's also home to the famous Ring Nebula, where a star has blown off most of its outer layers, leaving behind a remnant star known as a white dwarf. So let the bright star Vega lead you to Lyra, the harp constellation in the June sky. And if you see it as an eagle, or a diamond ring, or a llama, well, that's perfectly okay too. Here are the phases of the moon for June. Stay up to date with all of NASA's missions to explore the solar system and beyond at nasa.gov. I'm Preston Dykes from NASA's Jet Propulsion Laboratory, and that's what's up for this week.
And Dr. Z, Dr. Thomas Zerbuchen, and I would like to answer some of your questions. We got a question, which I think you and I only have one answer to. It says, what should I study in the field of space science, and why should you study it? And you and I have different reasons, so I'm curious to hear yours.
So first of all, should you study space science? Absolutely. It's a great subject area. And there's many different ways you can get into it. I actually believe the 2 of us have a different degree. Mine is a PhD in astrophysics. There's some others that I know that went to engineering and so forth. And for me, what's really interesting is as we build teams, these resilient teams that make these missions happen, it takes many of us with different backgrounds coming in and study whatever it is that you most excited about. For me, that was astrophysics, and I'm really glad I did that. I focused on the sun, but you studied something else, right?
Yeah, I studied planetary geology, and this question was one of the reasons I wore my Cassini-Huygens shirt today. I worked on the Cassini mission looking at one of Saturn's moons called Titan, and we had people who were geologists, people who studied the atmospheres, we had people who studied the rings of Saturn, we had people looking at the solar wind out in the vicinity. So you had all these people from all these different disciplines, and we were all space scientists, and all working together to really try to understand Saturn and its crazy system of moons. So to me, it's the best field because it's fun. There's so much to figure out. And with data coming in from new telescopes like James Webb, we're never
It's really about you personally. So how did you overcome it? And who helped you along the way?
I look back to my own personal experience and say, well, how did I as a young girl get involved when so few girls did? One of the things I really think about the fact that I had parents who hugely supported me. I had teachers who hugely supported me. And it wasn't until later in my career where I encountered obstacles and a lot of men who clearly thought I really didn't belong in the room. I got called little girl after I'd had a child by someone who actually worked for me. I did eventually encounter that kind of treatment, but by the time I did, I was a lot further on in my career. So I really think about how can we better support kids who may not have that support network of teachers and parents. How do we, as the science community, really reach out to kids and say, science is a great field. The other thing I really think about, and it's something I work on a lot at the Air and Space Museum, is when I was a kid, I looked for women role models. I looked for women role models, and they were so hard to find. So as we reimagine the National Air and Space Museum, as we're redoing all the galleries, I really think about whose stories are we telling, and are we telling stories so that every kid, no matter what they look like, when they come in the museum, they understand that people talent of all of our population.
Well, I really want to thank you for being a role model yourself. I remember introducing you to my daughter, and kind of the director of the Smithsonian, and of course, a distinguished scientist. What a role model you have been, and thanks for that. You persevered and pushed through. There's challenges ahead of us, and I really want to thank you for being just a role model for so many.
Thanks so much. This has been really fun, and I can't wait to do our next episode of Easy Science.
It's really an amazing world critter. It's been around for over 3 billion years. In 2016, Utah Lake exploded in cyanobacteria blooms. The problem is that many cyanobacteria produce toxins.
You may have heard it called blue-green algae, but it's really a kind of bacteria taking in sunlight to drive photosynthesis and giving off oxygen.
It actually requires quite a bit of lab testing to know whether or not it's a harmful organism. And what we're really worried about is people, pets, ingesting that cyanobacteria.
Dr. Kate Fickus is a harmful algal bloom scientist.
Man-made reservoirs. They're heavily used for recreation. They're heavily used for agriculture. And they're really important to the state as a resource.
In 2017, harmful algal blooms returned to Utah Lake. This time, officials used satellite data to identify troubled locations. But how can instruments up in space tell us about microscopic organisms in a lake down on Earth? By measuring their blue-green color. Landsat collects light in visible and infrared wavelengths. Cyanobacteria reflect more green light than plain water does, allowing Landsat to identify algal blooms.
From satellite, what we see is basically that primary pigment, which is chlorophyll A, but the color by itself could be misleading. A nice picture is not necessarily providing a set of quantitative data.
Algal blooms can look beautiful from space, but the numbers behind the images are the important part.
Each measurement is highly accurate, and it's very much corresponding to the number of photons that are leaving the body of water, which could be related to the biomass and the amount of firelight.
Dr. Nima Palavan is working with NASA and the U.S. Geological Survey to make sure Landsat users have consistent, accurate, and ready-to-use data about lakes and rivers. Water is difficult to study from space because only a fraction of the sunlight is reflected back to the satellite. But engineering improvements on Landsat 8 have leveled up its ability to measure the small signals from water bodies. After Landsat collects the data, it gets what Nima means here. To measure the amount of cyanobacteria, you need to know how much light reflected off the surface. But some of that light gets scattered by molecules in the atmosphere on the way to the satellite, lessening the signal received. And sometimes light that never made it to the surface gets scattered into the satellite, adding a false signal. Like removing the haze from a photograph. Atmospheric corrections leave you with a quantitative measurement of exactly how much light left the water, known as aquatic reflectance.
You want to look at the actual physical measurements to derive physically meaningful products from satellite data.
And that's the goal, to transform the raw materials into finished products so that end users don't have to build it themselves.
By providing aquatic reflectance products, you're majorly reducing the burden on satellite users.
Although it is still provisional, NEMA's aquatic reflectance data product is available for download from the USGS. Scientists like Kate Fickus convert the data product to maps showing the amount of chlorophyll A, helping local officials pinpoint where to test for toxins and warn residents.
I use Landsat and other remote sensing technology to help local health departments understand where there's a bloom, the magnitude of a bloom, and the size of the bloom.
The spatial detail is another benefit of using Landsat data. Each pixel is only a 30-meter square, the size of a baseball diamond, yet it collects data across a broad area. In other words, there is a lot of data at a fairly high resolution.
With Landsat, I can get into some of the marinas that are popular fishing and swimming spots in order to inform local health departments about making public health decisions.
For the 2017 outbreak, that's exactly what happened. Satellite data gave an early warning to local officials in Utah. The extra week of warning saved hundreds of thousands, and more are available for every spot on Earth. Landsat's highly calibrated data products, free to download and use, are making detailed Earth observation data more accessible to users and bringing a greater benefit to society.
What is a CubeSat? Unlike building blocks, units can be combined to make bigger CubeSats by stacking them into 2, 3, or even 6 units. Once in space, CubeSats can open up what they'll discover. CubeSats are also made from standard, low-cost parts that are easy to get and tested for launch safety. Some NASA launches carry spacecraft that don't take up all the space on their rockets, which leaves plenty of room for tiny CubeSats. Build a CubeSat, catch a rocket ride, and you become a space explorer.
Looking to power surface exploration on the moon, new imagery from the surface of Mars, and our newest flight directors. A few of the stories to tell you about this week at NASA. Systems are relatively small, lightweight, and can enable continuous power regardless of location, available sunlight, or other environmental conditions. This technology would benefit future exploration under our Artemis program. For more information about NASA's investments in space technology, visit nasa.gov/spacetech. NASA's Curiosity Mars rover has spent the stunning, but could also provide evidence that a major shift occurred in the planet's climate billions of years ago, which led to the dry conditions that we see today. Curiosity will celebrate its 10th year on Mars August 5th. For more information about Curiosity, visit nasa.gov/curiosity. NASA has 7 new flight directors. After completing a comprehensive training program, Heidi Brewer, Ronak Dave, Chris Dobbins, Garrett Hidd, Nicole McElroy, Elias Mirmo, and Diana Trujillo will oversee operations of the International Space Station, commercial crew, and Artemis missions to the moon. On June 18, Howard learned the influences and inspirations that put them on the path to NASA and what they experienced on their journeys to the agency. Some of the astronauts also gave advice and shared personal stories of hope and resilience to students who have aspirations of following in their footsteps. The 50-minute documentary is available for free to the public on NASA TV, the NASA app, NASA social media channels, and the agency's website. Vice President Kamala Harris and Second Gentleman Douglas Emhoff recently hosted an event at the Naval Observatory that included NASA STEM. Attended the event, including Tom Marshburn, who was the NASA technical consultant on the film, Stephanie Wilson, and Jasmine Mogbelli. Former astronaut and NASA Associate Administrator for Education, Leland Melvin, was also there. Our Office of STEM Engagement seeks to attract
celebrates LGBTQ+ Pride Month.
When you think of sea level rise and NASA, if that's the kind of thing you think about, I feel like it's only natural to imagine scientists poring over satellite data, trying to better understand what's happening and what the future might look like on our coasts, including right here where I live in the Hampton Roads area of Virginia. My name is Joe Atkinson, and I'm a science communicator at NASA's lab nuisance flooding just because of a high tide. But we'll get back to this area later, and specifically NASA Langley. The thing is, even as scientists are studying sea level rise, the job it is to work administrator for NASA's Office of Strategic Infrastructure.
First of all, I'd like to say thank you, Joseph, for the opportunity to speak to you about this. Sea level rise is a very major concern for us. We have about 2/3 of our NASA facilities are within 16 feet of sea level, and that comes to about $20 billion value of infrastructure that we have.
Now that long list of facilities includes Kennedy Space Center in Florida, Johnson Space Center in Texas, Stennis Space Center in Mississippi, Michoud Assembly Facility in Louisiana, Ames Research Center in California, and Wallops Flight Facility in NASA Langley right here in Virginia.
We have estimates that within the next 60 years or so, that there could be potential 4 feet rise in sea level. And so, therefore, we are trying to take measures now.
Now, in broad terms, that means moving to higher ground or, making facilities more resilient. At 2 of NASA's launch sites, resiliency equals the movement of lots and lots of sand.
For example, we've done some reconstruction work at Wallops and also at KSC, where we have stabilized the shoreline and the dunes there. And that's something that we have to...
You have to wonder, is this something that would keep Calvin up at night?
Well, it is at the top of our list, definitely at the centers that are on the coastal areas. We want to make sure that we are taking the necessary steps to ensure that in the future we have launch facilities, research facilities that can continue the mission of NASA.
Now, Calvin talked about her, but I kind of wanted to dig a little, and she is the director of Langley's Center Operations Directorate.
Certainly, we are a coastal center that's on the coast. We're surrounded by 2 rivers, the York River and the James River, and along with Chesapeake Bay. So a lot of opportunity for flooding and for sea level rise to present itself as a problem for our center. And so this is a big issue for us, and certainly one we've been addressing.
Tool is sort of like a crystal ball.
This tool is a great tool developed by our geospatial information systems folks, our GIS team, that allows us to visually picture the rising sea level and which facilities and areas are affected.
In 2011, following a study that highlighted some of Langley's biggest vulnerabilities, the center, which is actually NASA's oldest, it's just over 100 years old now.
In high vulnerable areas and building all of our new facilities and consolidating a lot of our missions into fewer facilities at our higher elevations. And for us at NASA Langley, our higher elevation is around 12 foot, so we're not very high here.
Further complicating the issue at Langley is a phenomenon hitting about 6.8 millimeters of relative sea level rise a year at Langley currently. The center isn't taking any chances. They can't pack up and head for the mountains, of course, but in addition to squeezing the campus onto the highest possible ground, they're also making really smart construction choices.
The study that we did in 2011, of course, recommended that we build all of our first floor elevators to 10-foot, 6-inch minimums, and that goes into our design requirements for all of our new facilities.
For Loretta, sea level rise isn't just a work concern, it's a personal concern too. She and her family live right on the water. But the communities in Hampton Roads are
You just never know, so it is a little personal and a little drives a little anxiety, but I'm very encouraged by certainly the work that the city of Hampton's doing, and I think the things that they'll do will continue to support
the San Francisco Bay. Now, when I reached out to Ames, they put me in touch with a guy named Garrett Turner. He is the Restoration Program Manager in the Environmental Management Division at Ames. And when Garrett thinks of sea level rise at Ames, he thinks back to 1998 and a series of storms that moved through the area. Now, this gave officials at Ames a big scare because it flooded the north.
A lot of employees, both civil servants and contractors, to go and put sandbags out, and then we were able to pump some of the water in the channels over a levee into Stevens Creek. After that, we kind of decided that we needed to have a proactive way of at least addressing big storms.
Now, much like Langley, Ames, which is the second oldest NASA Field Center, decided it needed to look to higher ground. That decision was based on 100-year sea level rise projections.
We are now requiring a much higher minimum elevation for a new facility that gets built. So we have these little popped up areas, and our master plan has envisioned taking facilities that are in that.
It's not just the bay that's a problem at Ames. There's an old system of salt ponds and levees nearby that date things, and it's not a problem that Ames can just deal with on its own.
Levee maintenance is outside of NASA's property, and we can't go and fix all of these and keep them from pouring water into NASA.
One thing they're doing is working with the local water district.
We're working on trying to, figure out how we can reinforce those levees and potentially raise them. And we have, a bicycling and walking trail, the Bay Trail that goes around.
They'll have to look to their neighbors on either side for help too.
If we protect the levees immediately in front of us, and they do others, to make sure that we can come up with a strategy that works for all of us.
One of those strategies,
we drained all the swamps. Now we're creating wetlands. It's kind of reversing what we did before. So it's all part of the same training.
We've had a little change would have me sitting in the water here. And even minor to moderate projections are pretty bad news for some folks right here in this neighborhood. All but the tallest vehicles. And so just as these coastal cities are having to deal with these wet realities, so too is NASA. When I set out to do this, I really had very little idea what NASA was doing to deal with sea level rise itself. Now, after talking to Calvin and Loretta and Garrett, Langley has subsidence. Kennedy and Wallops have beach erosion to deal with. Staying ahead of this stuff is obviously a big, big job that requires a lot of expertise, forest exploration, and aeronautics and earth science, even as the water keeps rolling in.
There's one thing that stands between us and the harsh environment of space, our atmosphere, the part of Earth that sustains all life. But here, in the closest town to the North Pole, it's slowly leaking away. A key factor in the search for life on other planets.
We have 35.
It's where we can access space directly, and where 100 tons of atmosphere escapes into space each day. This escape gives clues to how long an atmosphere will last, and ultimately, whether it stays around long enough to sustain life.
We're trying to understand is how did Earth's atmosphere evolve over time, and how do other planets that might be like.
It's an international mission to launch 12 rockets into the Earth's northern cusp. And Doug, he's the mission leader for the first 2 rockets of the campaign.
We don't want to waste our rocket to It'll take us 3 years to make the rocket, only 15 minutes to use it, and I don't want to waste my shot here.
He's using a sounding rocket, which is different from the bigger rockets that carry satellites and humans into space. It's a small suborbital rocket that flies briefly into space, collects real-time data for around 15 minutes, then falls back to Earth. It's affordable, quick to build, and can launch towards a precise point.
The major advantage is that you can launch into a target on the sky.
But there's a limited launch window and only one chance to get the launch every 15 to 30 minutes. And then they're monitored to see how fast the winds are carrying them.
Ground winds were 12 to 13 meters per second, gusting 17, which is way off.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this? So I think we're going to scrub for today. I'd like to thank everyone. I think it was a great performance. Thanks a lot.
This means that we are scrubbing this operation for today, and we'll try again tomorrow.
The mission is named Visualizing Ion Outflow via Neutral Atom Sensing 2, or VISIONS 2. In short, they're looking at how oxygen is getting enough energy to escape.
It's a good test of how atmospheric escape works. Earth's gravity should hold onto the oxygen, and yet we see this gas shooting off into space. We're trying to figure out how that works.
That is a science question that has been hanging around for 4 decades.
Fortunately, anyone can see atmospheric at noon, and you can only see it when it's dark during the day. It looks similar to the aurora that occurs at night, but when these iridescent colors dance at this hour each day, 100 tons of oxygen escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the ISCAT radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp. We can give advice that this is the right type of aurora.
This is the wall of science.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the North and South Pole, electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim where the cusp is. We have to wait for the cusp to come across our line of sight.
No.
Probably about a 60% chance of launching.
When we started seeing this really good
point, you can see the tension just rise in everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments.
Really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth, shedding light on how atmospheres throughout the universe change, evolve, and perhaps support life.
in my lectures a lot, there are always young people in the audience, and they always want to know when they're bringing it back. And I always say, I don't think ever. I think NASA realizes that they have two marks, so to speak, what's available, they can be made to coexist. We had to analyze what had been done by NASA in the past. Finally, we realized, well, we had to have a unifier, something that was very strong to hold it all together. So over the process of working on it, over the first month, I think we got simpler and simpler with our solutions so that they would work miles away on a T-38 or a rocket or a space shuttle. Inside of the A's and propulsion kind of upward thrust. Great simplicity, but still. The term came out of Florida in a newspaper down there, and it was meant to be derogatory, and I personally thought it was very derogatory. Eventually, over the years, the word became terrible, but it wasn't meant that at all in the beginning. When they started producing apparel a couple of years ago, they found out how young people in particular really like this program, and so they've allowed it to kind of come back to life on its own. It's validation, I think, of this sort of timeless approach that we brought to this. Space is about the future, and if we can still hang in there, and if it still represents that, then it's quite a victory, I think. Aesthetics aside, the goal was to do that over decades, and apparently it's got better legs today than it did then.
Studying Earth's atmosphere helps NASA scientists understand how to protect our planet. With data and continuous observation, scientists can monitor and see changes in Earth's climate. NASA scientists measure and study the ozone, aerosols, and water vapor in the stratosphere to enhance our understanding of Earth's climate. The Stratospheric Aerosol and Gas Experiment, or SAGE, is a series of instruments designed by NASA to observe stratospheric ozone, aerosols, and water vapor from space. Over the past 4 decades, the SAGE family of instruments have been critical in making laws in Earth's atmosphere. The data around the world institute an international treaty banning products containing harmful chemicals that destroy stratospheric ozone. The 1987 Montreal Protocol established the International Space Station, or ISS, and is now taking important measurements of gases and aerosols over 70% of the planet. The SAGE series of instruments takes measurements across the globe using a technique called occultation. Every time the sun or moon rises and sets, SAGE uses the light that passes through the atmosphere to measure gases and particles in that region of the atmosphere. From the ISS, this happens over 30 times per day. High-precision observations of ozone are vital. They demonstrate the effectiveness of the international agreements banning substances harmful to the stratospheric ozone layer, our planet's natural sunscreen. The currently observed trends in stratospheric ozone recovery are very small. An accurate assessment will require continued measurements that are both precise and stable. SAGE 3's solar occultation method provides a measurement of ozone that is inherently very stable and highly precise. It benefits from its predecessor's 40 years of experience with this measurement technique. Aerosols are tiny solid and liquid particles suspended in Earth's atmosphere, such as ash from volcanic eruptions and wildfire smoke. Each day, SAGE aerosol measurements form a visual band around the Earth. Scientists gather the daily measurement bands because how changes in the stratosphere are linked between latitudes. These measurements help scientists better understand how the aerosol particles spread around the planet, if they cause warming or cooling of the atmosphere, then darker colors. The area below the data that looks like an arch is the tropopause, which sits right below the stratosphere. SAGE detected the dramatic increase in spread of stratospheric aerosols from the southeastern Australian bushfires. The Rakoki volcano eruption emitted the most sulfur dioxide gas into the atmosphere in the past decade. After the eruption, SAGE-3 detected an enhancement of stratospheric aerosols over the north. NASA and SAGE will continue to help scientists understand Earth's changing climate, allowing us to better protect our planet.
A ship, and it's just very isolated. Like, that ship is really your whole world. Water that can open up underneath your feet. As we were transiting through the ice, we were searching for a suitable ice floe, something that was thick enough that could support us working on something.
While there wasn't enough ISAT-2 data for MOSAIC or the multidisciplinary drifting observatory for the study of the Arctic climate to use, Dr. Nathan Kurtz and the team were able to locate an area with the right amount of sea ice thickness by using different methods. Likewise, scientists often use various methods to measure why take measurements of the same thing using different methods? And how does measuring sea ice thickness relate to tree height? Let's take a closer look at the Ice, Cloud, and Land Elevation Satellite, or ISAT-2. Its main purpose is it also measures tree heights as it orbits photon counting lasers and algorithms developed to differentiate what environments they are measuring. An algorithm is a step-by-step procedure for solving a problem, a number of steps. Claudia Caraballo was the deputy lead for the Flight Science Receiver algorithms, one of many subsystems of the Atlas instrument.
On the ground for ISAT-2 are tailored directly to address that characteristics of the surface. So they are tailored to sea ice and vegetation. The coherence of those photons when reaching those surfaces changes, so the algorithms need to be specifically tailored to the surface type. Of course, comparisons against other data sets help you, and sometimes you need the help of an additional data set as you're processing.
When I was on MOSAIC, we took specific measurements that are useful and will be used. By combining multiple measurements together, we're able to quantify and see whether ISAT-2 is making its measurements accurately and how it's needed to be done.
One of the ways that you can actually figure out if ISAT-2 is actually measuring the right thing is to compare it with the observations that are being collected by other means. For example, airborne campaigns, other satellite data, and see what the surface looks like. You can look at how things are changing in different seasons.
Whether it's sea ice thickness or tree height, comparing data collected by different missions and field campaigns allows scientists to better understand how the instrument works. Dr. Laura Duncanson uses LiDAR data to create 3D maps of forests, and Dr. Nancy Glenn is currently looking at various ways in which tree height data collected by ISAT-2 and Globe observers can be utilized. For both, tree height data adds to our understanding of Earth's systems.
Of course, we can't go out into the woods all over the planet and measure every single tree on the ground. So for ISAT-2, these estimates of tree height, we don't know exactly how precise they are, how good they are in all of the different forests around the globe. There's a lot of variability in forests.
Just like how taking field observations and airborne data collected of sea ice thickness can act as supplementary data to ISAT-2, tree height measurements collected in the field can also be used to do the same. This supplementary data can help scientists account for variability between different environments when looking at measurements collected by satellites. As mentioned, tree height measurements can be taken in different ways. One method is to use trigonometry to estimate the height of a tree. This is the method that students and citizen scientists use. By measuring the distance to the tree, along with angles A and B, using a handheld clinometer or the one built into a smartphone, observers can calculate the height.
Having people go into the woods and actually measure tree height to compare to the satellite estimates of tree height gives us a sense of how reliable those tree height estimates are, and maybe some ecosystems that they're particularly good at doing tree height or particularly challenged doing tree height.
Now we know that by taking measurements of the same thing, using different methods can help scientists. Taking tree height measurements adds a whole new data set for satellites and instruments such as ICESat-2 and JEDI to compare with. These measurements also provide content that only an observer on the ground can provide, like recent changes, including drought, fire, invasive species, and more. Now that leaves the question, why do scientists study trees?
So for decades now, we've had really good maps of where there are forests and where there aren't forests, but we've never before known how tall the trees in those forests are. And this is a really critical piece of information because it tells us not only, of course, how tall the forests are, but how much above ground woody carbon they store. Forests, carbon stops on the Earth's surface. And if we cut down and burn forests, we essentially are pushing more carbon into the atmosphere. And if we allow those forests to regrow, we're sucking that carbon out of the atmosphere. But we don't know right now how much carbon is where in Earth's forests because we've never had that third-dimensional measurement of Earth's forests, which is so tightly linked to its carbon content.
Using tree height not only helps scientists track how much carbon is getting released into the air, but can also be used in other ways.
Tree height is really important for us is that we're interested in knowing how tree height is affected by increased CO2 or increased temperatures or decreased temperatures. And that gives us an indicator for making predictions about trees in the future. What we're interested in is that trees and the differences in tree heights provide some level of what we call structural diversity. And structural diversity can be really, really important for a health of an ecosystem as well as provide habitat for a variety of different types of animals. So we're using NASA resources, NASA airborne data, as well as satellite-based data like ICESat.
Many Earth-observing satellites, such as Landsat, can only see a top-down view of Earth. This information comes in the form of two-dimensional images made up of pixels between the size of 30 meters squared to 500 meters squared. But now, with JEDI on board the International Space Station and the launch of the ICESat-2 satellite, are able to see height added to this top-down view of Earth. By taking and submitting tree height observations, citizen scientists and students can help scientists and researchers, not just by providing measurements from different ecosystems, but by providing a different type of data. What seems like such a small piece to contribute can help scientists across the world.
The Globe Observer tree observations essentially
a great intersection. More data, the better. But also the connection, right, is that the connection between scientists and the community and scientists understanding what's important to our communities and being able to engage and learn from one another.
There is a large part of collaboration between the instrument scientists and everybody working on every aspect of the Atlas instrument, and the mission scientists and his deputy, everyone else in all the universities. Citizen science is really important to get the community involved, to motivate everybody to be more informed about the science and also perhaps motivate a crowd of new scientists.
All of this is important because one, it's the pursuit of answering questions about our natural environment. Our natural environment is changing very rapidly.
A tree height measurement that's taken by citizen scientists could be useful for us.
It's really important for us to monitor what is here now so we can document that, but also use that in models to predict what might be here in the future.
To learn more about Globe Observer, check out the website at observer.globe.gov and download the app to start taking your own observations today.
Today, GPS and similar navigation systems use satellites in space to help you navigate where you want to go here on Earth. Tomorrow, these same satellites will transform navigation in space as well as making life on Earth safer, healthier, and more productive. And they will even help navigate missions to the Moon and spacecraft on the way to Mars. This will be accomplished through the international collaboration and capability called the Space Service Volume. Worldwide, there are 4 global navigation satellite systems and 2 regional navigation satellite systems, collectively known as GNSS. These navigation constellations include the United States' GPS, Russia's GLONASS, Europe's Galileo, China's BDS, India's NAVIC, and Japan's QZSS. Individually, these constellations can significantly improve navigation for spacecraft in low Earth orbit, like the International Space Station, or missions that measure climate change and map the Earth's surface. But for the spacecraft located in higher orbits, in a region we call the Space Service Volume, navigation is more challenging. The Space Service Volume stretches from 3,000 to 36,000 kilometers above Earth. Most navigation satellite orbits are inside this region and broadcast their signals toward Earth. However, it is challenging for other satellites, like weather or communication satellites at the top of the Space Service Volume to receive these signals. Users on the other side of Earth receive weaker signals from navigation satellites because of longer travel distances. Additionally, the Earth blocks most of the navigation satellite signals. In response, engineers have developed special technology to navigate with weaker and fewer signals in view. But this does not overcome all of the challenges. Because users in low Earth orbit are below the navigation satellites, the individual constellations can guarantee lots of signals for missions like space station. In the upper reaches of the Space Service Volume, users receive significantly fewer navigation signals and many times no signals at all. This unified system is called the multi-GNSS Space Service Volume. So how do we get all of these constellations working together? The International Committee on GNSS, the ICG, sponsored by the United Nations Office of Outer Space Affairs, is leading collaborative efforts to ensure that all of these systems are interoperable through the creation of common definitions and specifications. Operating together, this combined system of navigation satellites will be transformational for missions operating within and above the Space Service Volume, significantly improving navigation performance and enabling spacecraft to navigate autonomously without any direction from the ground. This technology enables accurate pinpointing of extreme weather, like flash floods, tornadoes, and hurricanes, crucial for public safety and more accurate weather prediction. It will fuel future advancement in observing, communicating, and working in space, even extending all the way out to the moon. Like
I am my authentic self.
I am a queer woman.
I am a transgender woman.
I am a lesbian.
I am gay and I'm my authentic self.
I'm a parent of a transgender son and I'm very proud.
Ever since I was a little kid, I felt that it was really important to be my most authentic self, especially knowing that this was my dream. Queer people can dream big.
Exploration needs to be for everybody. Every person, every kid, if they can see themselves, the astronauts that we send out in space, but also the teams that make that possible, that we're doing our job. We're doing incredibly difficult and complicated things. We want people that look at things from a different perspective that can bring us new ways of solving problems, and diverse and inclusive teams do that.
If someone is in the closet and they see people like me doing our jobs, being effective at our jobs, I think that's the biggest encouragement that I can give them is to show I can be my true self and I can be out with one another.
That comes from being your authentic self. You can be that.
I am non-binary. I am gay. I use they, them. There was one instance where I was participating in a candidate lunch, and they actually also use they, them pronouns. See someone else in the room using those pronouns, and I made sure to introduce myself with my pronouns so that they could know. you're not the only one here. There's someone here who understands you, and
me, I get to work with smart and capable people, and our job is to explore outer space and to uncover the mysteries of the solar system as a daily.
Our mission here at NASA becomes more effective.
We're all different, and we should all accept each other for our differences, because that's what makes us special.
It's really important that we can show that visibility is safe, and that you can absolutely be a part of the team and loved and valued for who you are.
It's never too late to be yourself. It's never too late to find your happiness. I am NASA.
I am NASA.
I am NASA.
I am NASA.
Humanity has always been interested in exploration. We really want to go to the moon. We have got to figure out a way to keep our propellants cold long enough. My name is Monica Guzik, and I have the coolest job at NASA because I work with cryogenics. Cryogenics is the study of things at very low temperatures. We've got electrical connectors we can plug into, so we want to store things like oxygen or hydrogen, but raise the pressure really high. So instead, if we make them really, really cold, they turn into a liquid, so they're way more efficient to store. So this is going to be a liquid oxygen test. I always knew I wanted to be an engineer since I was a little girl. My dad was an engineer, and I just thought engineering was so cool. We were going to put insulation over this. Ended up getting a summer internship here at NASA Glenn Research Center in Cleveland, and just really sort of fell in love with NASA. Cleveland is the rock and roll capital of the world. I really enjoy rock and roll music, so I try to go to a lot of concerts. When we improve cryogenic technologies for space applications, it always has a trickle-down effect to the Earth. Now we're rolling into the Artemis generation, and we're still doing that.
Looking to power surface exploration on the moon, new imagery from the surface of Mars, and our newest flight directors. A few of the stories to tell you about. These systems are relatively small, lightweight, and can enable continuous power regardless of location, available sunlight, or other environmental conditions. This technology would benefit future exploration under our Artemis program. For more information about NASA's investments in space technology, visit NASA. Imagery captured of rock formations in this transition zone is visually stunning, but could also provide evidence that a major shift occurred in the planet's climate billions of years ago, which led to the dry conditions that we see today. Curiosity will celebrate its 10th year on Mars August 5th. For more information about Curiosity, visit nasa.gov/curiosity. NASA has 7 new flight directors. After completing a comprehensive training of the NASA-back astronauts, recounting the influences and inspirations that put them on the path to NASA and what they experienced on their journeys to the agency. Some of the astronauts also gave advice and shared personal stories of hope and resilience to students who have aspirations of following in their footsteps. The 50-minute documentary is available for free to the public on NASA TV, the NASA app, NASA social media channels, and the agency's website. Vice President, several current, Leland Melvin was also there. Our Office of STEM Engagement seeks to attract and engage a diverse group of students to STEM fields, to contribute to NASA's work, and to build a diverse future STEM workforce. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twine.
What is unique about the surface of the moon? Well, the moon is quite unique from the Earth. It has no atmosphere. There's no air to breathe. What that means is that the processes that have occurred on the moon are all preserved there in the rocks. For instance, if you look at the moon from the Earth, you may see circles. Those circles are impact craters. So let me show you. Except, making craters is really dirty business. I need my crater-making poncho. Now we're ready. Let's pretend this is the surface of the moon. It looks a lot like this. That's one crater, but the surface of the moon has many more.
Oh, that was a good one.
And they have water ice trapped there, and they never see the sunlight. That's good for science, and could also be a resource that helps our astronauts survive. Why study moon rocks? Well, besides the fact that rocks are awesome, each rock is kind of like a person. It has its own fingerprint. We talked about impact craters. That's recorded in the rocks. Whether or not ice or water has been near there, that's recorded in the rocks. It tells us the history of the moon. What tools will be like rakes and shovels to help us find the right kind of material to bring home? Eventually, we could be using tools more like this. This tool is an X-ray fluorescence spectrometer, or XRF. An XRF basically shoots X-rays that are designed so that they can help us move around on the surface. Well, this tool is 3D printed, but this is just a model of an XRF. But right now, we have to practice here on Earth. The way we do that is we talk to them in the laboratory and classrooms, and we also take them out into the... Right now, our plan is to send crew to the surface of the moon once per year and bring more supplies to the surface so that we can explore more and more of the South Polar region. That is a great question. The first thing that's going to be very different is that during Apollo, the sun was overhead, but at the South Pole, the sun is always going to be right on the horizon. That means we'll have really long shadows in areas that are very dark. It's going to be very different. We really are exploring a brand new terrain where no one has ever been. The studies we'll be trying to do are looking at and understanding perhaps the water cycle of the moon. And we really want to understand the processes that lead to that water being preserved there. Ooh, that's an intriguing question. First of all, we can see fairly deep into the interior of the moon by looking into craters. That's kind of our natural laboratory for getting at the inside of the crater. Every time a crater forms, there's an explosion that moves rock up and out from inside of the moon. So our astronauts walking around the rim of the craters can pick up rocks that came from deep inside. So the bigger the crater, the deeper the rocks. Well, in fact, we are aiming for farther out. Eventually, we want to get to Mars. But first, we're going to go to the moon and learn some really important answers to questions that will help us survive the trip out to Mars. Because I guarantee you, I'm going to have a lot of questions for them when they get back.
Do you have a question for NASA? Send your questions to our experts using hashtag AskNASA.
This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine program, the F-18, an observation and occupation, one of the more challenging.
Right now, we are looking at the dawn of a new era of aviation.
Your Air Force has continually developed
The development of new power in the air has brought about terrific speed.
Driving a subsonic airplane at speeds for which they were never designed would be a hazardous business.
Knowledgeable men were seriously wondering whether man could ever fly faster than the speed of sound.
It remains for the high-speed flight program to attack these problems with scientific studies of a new kind.
Rifle and artillery shells have been traveling supersonically for many years. The X is shaped like a 50 caliber bullet.
Blazing through sound barriers and now heat barriers, the Bell X-2 reaches the unheard-of speed of 1,900 miles per hour.
The D-558 was the first American aircraft to use swept-back wings and stall fences. The primary mission of the X-3 was thin wing research. The X-4 was its classical horizontal tail. The X-5 could sweep its wings in flight.
Pilots achieved a 7-to-1 ratio to make the United States Air Force played a vital role in holding the line against communist aggression.
Step by X-15. This was a logical step in the research aircraft program. The first hypersonic aircraft.
What is the role in space?
The hypersonic flow of air would heat the leading edges of the plane to 1,300 degrees Fahrenheit. How could the pilot control the aircraft in air so thin that normal aerodynamic control would be impossible? No engine like this had ever existed before.
50,000 pounds of thrust in a single chamber had to be controllable at the pilot's discretion.
The X-15 pilots flew to study the physiological aspects of high speed and high altitude flight. The data gathered proved to be invaluable to follow-on missions beyond the Earth's atmosphere.
They have dramatized the potential of piloted high-performance aircraft in a space environment at a time when much of the world's gaze was turned toward orbital flight.
The aeroplane has become an important means of commercial transportation and a decisive weapon of war. Your transportation helps our economy.
The United States is only about 5 hours wide.
Research programs investigate flight at ever greater speeds as time and distance shrink.
Supersonic transport must be durable, and it cannot itself cost too much. The controversial XB-70 gathers invaluable data on stability and control characteristics.
We were flying through YF-12s with a whole lot of supersonic high-temperature X-15 surge. We had the F-111 attack airplane, which contributed greatly to knowledge of transformer regime.
A cross-country flight that would take you minutes instead of hours.
The X-43 is a revolutionary new kind of airplane. What we want to do with this is prove that hypersonic flight with an air-breathing engine is possible.
2 Mach 3.
Though the technology exists for aircraft to fly at speeds faster than the speed of sound, today's aircraft don't.
The aircraft is flying from New York to Los Angeles. The sonic boom will be heard consistently across the country. We're talking about commercial operations. You're having, 40 in a day.
Would be breaking windows or at least annoying a lot of people.
We can in fact shape the airplane in such a way that we can shape the sonic boom and sound it. This project is looking for instrumentation for the air crew to see where the airplane is booming and what it's up. It's a real-time map display overlaid with the boom showing where it's hitting the ground.
Supersonic.
It's that pull-out that puts the quiet boom out on the area of interest.
Extra 3.1. Spike 3.1.
The end goal is to create a quiet supersonic aircraft.
With the F-59 program, we're going to be gathering a series of data from communities around the U.S. relating people's response to the noise to the sonic thumps. We're hoping.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration. Together, you and I must make our new agency
The most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything. We can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
It's sleek, high speed. and of the more challenging missions that the vehicle.
Inventors thought that flight control could be achieved by a pilot simply shifting his weight back and forth. The Wrights, on the other hand, knew that controlling the plane would be key to successful flight.
Release brakes, throttle to activate. Watch exhaust. Watch nozzle position. Check engine pressure ratio now. And all this time, steer down the runway. First nose wheel steer, then rudder. Lift nose wheel at just the proper speed to fly off in the least ground roll.
Today, man copes with a highly complex environment, with physical abilities no better than he has ever had.
Greater demands on the air crew call for ever closer relationships between man and machine.
Until now, all flyers have used the force of their muscles, multiplied by gears and rotors, to adjust wing and tail surfaces.
Your landing gear and flaps are operated hydraulically.
It's about 45 pounds of force to get that stick tall. It's a very athletic thing.
An advanced flight control system called the Digital Fly-by-Wire System has been installed by the Flight Research Center in a modified F-8 jet aircraft.
The pilot of this experimental aircraft need only indicate the desired flight path to a computer, which then calculates and actually executes the control changes needed to stay on course.
The heart of the control system is a digital computer and an inertial measuring unit that were developed for the flight control system of the Apollo lunar module. Use of this kind of control system would make air travel of the future smoother and safer by reducing aircraft vibrations caused by turbulent air through automatic response from the computer to the aircraft controller.
We used an F-111 for integrated engine control.
Further mechanization hopes to make more optimum blending of airframe and propulsion system control.
A computer-controlled flight system, along with some new control services, allow this modified F-16 to maneuver laterally, change altitude without pointing its nose, and perform other unconventional maneuvers.
The Deke system is full authority digital electronic control. The fastest calculation we've been control is 24 milliseconds.
At Dryden, we have been working integrated controls here over 100 years, so we decided to see if we could extend our integrated control approach to let the engines do all of the flight control.
When Gordon Fullerton lands an F-15 and he hasn't touched the control surfaces, all the people who said it was impossible suddenly don't have a lot to say anymore.
This will be invaluable in military and commercial aircraft of the future.
We can bring it in not for just a survivable crash landing, but a precise normal landing, which is what we did, with absolutely no motion of any external flight controls. Purely by manipulation of the engine side.
Using neural networks to identify aircraft stability parameters and to optimize control performance during test flights will reduce development and program costs.
A neural network is a computer program comprised of a series of examples. And in our particular case, these examples are previous flight data.
Power-by-wire actuators only draw power from the aircraft is maneuvering, so that saves a great deal of energy, which an aircraft translates to fuel.
This new software allowed the aircraft's flight control computer to minimize drag by automatically determining the best setting for thrust vector nozzles and aerodynamic controls. Thrust vectoring is the ability to direct an aircraft's thrust for direction control, rather than relying on conventional control surfaces alone. The Intelligent Flight Control experiment, to be tested in early 1999, seeks to enable aircraft control systems to adapt to unforeseen changes in aircraft operating conditions.
In addition to advanced controls research, the FAST system allows for simulating system failures.
Data from NASA's Integrated Resilient Aircraft Controls, or IRAC project, will be used to design and develop aviation systems better enabled to safely fly and land damaged aircraft.
One promising technology that may make it possible to improve both aircraft safety and performance is active stabilization of rudder using advanced flight control systems.
raccoons have to do with climate change? Well, did you know that if the levels of carbon dioxide go to the levels they're predicted by 2050, raccoons are going to start moving further north into colder areas. And while raccoons are cute, they cause a lot of damage when they move into ecosystems where they don't belong. So we're going to talk about 5 things satellites can do to help with climate change. Number 1, it helps scientists see the big picture. In a country as large as Canada, we need satellites to keep track of the whole country. We can look at the land, the water, and the atmosphere and see how they interact and change over time, including the impacts of climate change. Number 2, satellites help scientists study clouds and their impact on climate and weather. You may not know it, but those cute, fluffy clouds could actually have a bigger impact on climate change than greenhouse gases. Number 3, measure carbon monoxide concentrations. Satellites help us measure the amount of carbon monoxide so that we can check if those anti-pollution measures really work. Number 4, monitor signs of coastal erosion. Canada has the longest coastline in the world. Coastal erosion puts roads, the homes of people who live nearby, and marine ecosystems at risk. Number 5, monitoring the ozone layer and the substances that can damage it. A thinning ozone layer leads to increased UV radiation, which increases our risk of sunburns and skin cancer.
And navigation services and technologies to meet tomorrow's challenges. SCAN is for space information for the process of scientific discovery. Our extensible and expandable communication and navigation infrastructure provides a resilient space framework that can meet the growing requirements of our users. It will enable autonomous satellite networks, and optical communications will increase our ability to send and receive data to the vastness of space. We are developing these and other technologies to advance explorations of Earth, the lunar region, and beyond. Spectrum, the medium that enables communications and navigation. Through coordination, we ensure efficient use of this limited resource. We work with P&T partners to provide space missions accurate position and timing information. The most exciting part of this journey lies ahead, collaborating with commercial industry on major advancements in space communications. Our next generation of visionaries are creating a bright future, enabling Artemis lunar communications and a pathway to Mars, NASA space communications and navigation, SCAN, exploration enabled.
I am gay. I am my authentic self.
I am a queer woman.
I am a transgender woman.
I am a lesbian.
I am gay and I'm my authentic self.
I'm a parent of a transgender son.
Harry Potter.
I knew I wanted to be in science ever since I was a little kid. I felt that it was really important to be my most authentic self, especially knowing that this was my dream. Queer people can dream big.
Exploration needs to be for everybody. Every person, every kid, if they can see themselves, the astronauts that we send out in space, but also the teams that make that possible, then we're doing our job. We're doing incredibly difficult and complicated things. We want people.
They accept me 100%. We're all together working on this.
Who I am is enough. And when you resonate that kind of pride within yourself and you exude the love that you have for yourself, before you know it, you've got a tribe of people who are just motivating and uplifting one another. That comes from being your authentic self. There's someone in the world struggling like you who needs to see someone like you to keep going. There's someone who needs an example, and you can be that.
I am non-binary. I am gay. I use they, them.
There was one instance where I was participating in a candidate lunch, and they actually also use they, them pronouns. And it just felt really nice to see someone else in the room using those pronouns, and I made sure to introduce myself with my pronouns so that they could know you're not the only one here. There's someone here who understands you and really just wants the best for you.
It requires some bravery, but take the leap. Just be honest, be yourself. And if you are yourself and they accept you, then you've found what you need. I've learned how to be confident myself, and I've also sort of established myself here. People know me. I get to work with smart and capable people, and our job is to explore outer space and to uncover the mysteries of the solar
true self, in love with my wife, and if we can be ourselves, our mission here at NASA becomes more effective.
We're all different, and we should all accept each other for our differences, because that's what makes us special.
It's really important that we can show that visibility is safe, and that you can absolutely be a part of the team and loved and valued for who you are.
It's never too late to be yourself. It's never too late to find your happiness.
No matter what your identity is in the community, that there's going to be a place for you, and there's going to be a place for you to not only just be here, but to succeed and to thrive. I am a queer woman, and I am NASA.
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 Simplicity, but still movement.
Roger, roll, Discovery.
The term alone came out of Florida in a newspaper down there, and it was meant to be derogatory. And I thought producing apparel a couple of years ago, they found out how young people in particular really like this program, and so they were allowed to kind of come back to life once. Validation, I think, this sort of timeless approach that we brought to this space is about the future, and if we can still hang in there and it still represents that, then it's quite a victory, I think. Aesthetics aside, the goal was to do that for decades, and apparently it's got better legs today than it did then.
rocket dress rehearsal here in Florida. It is not launching today, but before a rocket like this one starts launching missions to help assemble a space station in orbit around the moon, NASA is first enabling a small CubeSat called Capstone to test out that same lunar orbit. And we're taking you live to New Zealand for that Rocket Lab launch next. Less than an hour, Rocket Lab's Electron rocket will lift off from Launch Complex 1 on the Mahi Peninsula in New Zealand. It's dark out there, just a few hours after sunset for our friends in New Zealand, which time-wise, right after 9 p.m. local time. Liftoff is 9:55 p.m. local time. That's 5:55 p.m. Eastern time. And if all goes well, that Electron rocket that you see on the pad there will light up the night sky carrying NASA's Capstone spacecraft towards the moon. Back here in Florida, thank you for joining us for live coverage of the Capstone launch. I'm Daryl Nail, and as I mentioned earlier, that's NASA's moon rocket on the pad behind me with the Orion spacecraft. It's on Launch Complex 39B, and preparations are being made to roll that SLS rocket back to the Vehicle Assembly Building on a gigantic mobile crawler, currently scheduled for Friday. But when the launcher and moon rocket return to this pad, they will be ready for Artemis 1, an uncrewed test flight on an orbit around the moon. That has yet to be scheduled. But now, back to today's mission. Before Orion goes to the moon, we're sending Capstone first, a satellite the size of about a microwave oven, which will demonstrate a new way to guide a spacecraft around the moon without relying on Earth-based communication. Capstone stands for Cislunar Autonomous Positioning System Technology Operations and Navigation Experiment. It's a mouthful, and here are some fast facts about it. It's a 12-unit CubeSat, and as you can see from this animation, it has solar arrays and thrusters, small ones at the bottom. The dimensions without the arrays are just 1 by 1 by 2 feet, or 34 by 34 by 61 centimeters, and it weighs just 55 pounds, or 25 kilograms. And it doesn't. Let's get an update on preparations. There's a little bit of a delay between us. It's not nearly as long as the time difference, though. 16 hours you're ahead of us here on the eastern coast of the United States. But I say to you, good evening, and for us, good morning.
Thanks, Daryl. That's right. Welcome to quite literally the future of space exploration. It is just at T-minus 51 minutes to the countdown, and here in New Zealand, I'm joining you live from the Rocket Lab Mission Control Center in Auckland to take you through today's launch of the Capstone mission from our country's eastern shore of the North Island. Our Rocket Lab launch operators are making their way through the count with checks on the systems and the health of the Rocket Lab Electron launch vehicle and Photon lunar upper stage, as well as the Capstone spacecraft integrated to Photon. All three are sitting on the pad at Rocket Lab Launch Complex 1, as you can see there, on the Mahi Peninsula, from where we will launch the Electron rocket on an eastern trajectory over the South Pacific Ocean. Now, liftoff is currently scheduled for 21:55 local New Zealand time, or 09:55 UTC. In Eastern Daylight Time, that translates to 5:55 in the morning for you, Daryl. Sorry about that. And for Pacific Daylight Time, liftoff is scheduled to a even unfriendlier 2:55 a.m. Our latest status update from our weather official and mission control reported clear skies over the launch site. The weather is nice and still this evening, with the probability of violation very low, meaning we are very close to that launch liftoff. Now, over the past few hours, Rocket Lab's launch crew on the ground and in mission and range controls have been readying the launch pad with vertical and avionics checks with the rocket and have loaded Electron with its propellant types, kerosene and liquid oxygen. So right now, with just about 50 minutes left to lift off, all systems are go for launch, and I'm going to hand it back over to you at Kennedy, Daryl.
All right, great report, Muriel. And quick question for you. Why launch from New Zealand?
Daryl, if you're looking for a launch site anywhere in the world, the ideal location is an island in the middle of the ocean, which New Zealand as a country makes a great option for. And if you're going to launch east, which you would like to do because you get that free push in the same rotation of the Earth, then the east coast of New Zealand is a great place to be, and Mahia on its peninsula jutting out over into the coast is a wonderful spot because we have very little air and marine traffic. So it's really a one-in-a-million location.
It certainly is, and it's incredibly gorgeous, especially during the daytime, and hopefully in the future we can show you a daytime launch as well. Well, we've got a lot of cool stuff to show you coming up in our pre-launch show, as well as some great interviews. First, we'll take a closer look at the Capstone mission itself, the very first spacecraft to fly as part of the Artemis program. Plus, we'll speak to an expert about this, the rectilinear halo orbit. What do we expect to learn, and how will we use the data? And from Capstone to Gateway, we'll talk to a NASA expert about the latest on plans for a lunar outpost where NASA astronauts will dock before going down to the surface of the mission for the Lunar Gateway.
Before NASA's Artemis astronauts go to the moon, a small spacecraft called Capstone will help lead the way. The Cislunar Autonomous Positioning System, Technology Operations and Navigation Experiment will test a unique lunar orbit that has never been flown before. This orbit will be home for NASA's Gateway, the future space outpost that will support visiting astronauts on their way to the moon and beyond. To help prepare for Gateway operations in this orbit, Capstone will fly the path first. The mission will be led by small business partner Advanced Space. Rocket Lab will launch the spacecraft. The gravities of Earth, the Sun, and the Moon will help propel it into deep space. As it nears its destination, Capstone will use its propulsion system to enter an elongated path around the Moon. The spacecraft will orbit between the gravities of Earth and the Moon in a precisely balanced dance. For 6 months, it will gather data about this crown-shaped trajectory known as a near-rectilinear halo orbit. The path provides an unobstructed view of Earth as it orbits the Moon's poles and allows for continuous communications with ground-based control centers. Capstone will also demonstrate a new onboard navigation system. It will communicate with NASA's moon-observing Lunar Reconnaissance Orbiter satellite to calculate its position. The technology could allow future spacecraft to pinpoint their location without having to entirely rely on tracking from Earth. Capstone's flight will demonstrate how this unique lunar orbit can support future spacecraft around the moon, helping to launch a new era of human space exploration.
Now is Dr. Jeff Parker, the chief
factor satellite. It's a full spacecraft in a small body. It's got a propulsion system down here. It's got an antenna that talks to the ground here. This is the antenna that talks to the Lunar Reconnaissance Orbiter, another satellite in orbit about the moon. Solar panels. These extend, so this isn't a fully unfurled solar panel, but yeah, that's right.
It's about right. The microwave oven was the analogy given, and it certainly looks like it's exactly that. Tell me, this is going into this near rectilinear halo orbit. How will it do that, and what's it going to do when it's there?
You bet. So the near rectilinear halo orbit is a challenging orbit to say, but it's a really impressive orbit for its operations. We use a low energy transfer to get this guy into that orbit, and it uses very little fuel to get there. When we get there, this is a model of what the orbit looks like. Hopefully we can see that.
Yeah.
So Earth is in the middle, Moon goes around, and we form this crown shape about the Earth there. And then this orbit is just fantastic for what it needs to demonstrate. There we go. And it takes very little fuel to get into this orbit using this certain type of transfer to get there. And then it takes very little fuel to get down to the surface of the moon. We might even be able to use it to go out to asteroids. It's a gateway, and we're demonstrating this as the gateway for the Artemis program.
We're seeing a beautiful shot of Capstone right there on the top of the Electron rocket. You're with Advanced Space. We've got that team as well that's online tonight. They'll really start working when the mission fires up. What challenges do you expect to find once this gets into its orbit?
So nobody has ever flown one of these orbits before. Now, we have demonstrated this in simulation many times. We're ready for anything, even contingencies, but space flight is challenging. So we're ready for anything. We're going to go head on and teach NASA every lesson we learn.
And there's your team waving at us live from Colorado. That's the Advanced Space Headquarters in Colorado, where Capstone Mission Operations Center is located. A lively bunch tonight. Again, they're going to get working in 6 days.
That's right, that's right. I love this launch. It gives us 6 days to prepare between launch and the time that our team picks up the satellite on the way to the moon.
So tell me, what other lunar orbits were considered when you were first developing this? Because, you know, NASA gave you the funding for this mission and then said, hey, check it out for us.
Oh, sure. Yeah, we looked at a lot of different orbits like this, and they all had to have the same kind of requirements. So they all had to have a low fuel requirement to get this satellite, which only has so much fuel, into that orbit. Has to be a gateway, just like NASA's doing. And then NASA in general has tested out a lot of different orbits. We've landed on this NRHO because of its terrific viability.
And with this spacecraft here, when it maneuvers, it's these small little jets here at the bottom, is that right?
Yeah, that's right. Yeah, it has enough fuel to do everything we need. We have enough fuel for an extended mission as well. It's a monopropellant hydrazine system. Yeah, full spacecraft.
And so in order for it to know where it is, are you telling me this antenna up here is what communicates with the LRO?
Yeah.
Another spacecraft.
That's right. Our spacecraft has 2 radios, one to talk to the Earth, which is a conventional approach, and one to talk to another spacecraft, the LRO. And this is a reverse radio for LRO, so it's perfect to talk to LRO. We're going to demonstrate navigation in a couple of ways. One with communications with LRO, which should be enough to navigate the spacecraft. Another one to do one-way communications with the DSN, which is a future advanced navigation technology. Everything we can do to try to help enable future lunar exploration. We envision a future that has a lot of missions in orbit about the moon. We're trying to help that out.
Absolutely. Thank you for bringing this. This is great, and for describing it, Jeff. But now we're going to go to the real Capstone. You see on your screen there, and check back in with the launch team and our commentator, Muriel Baker. How are we looking so far, Muriel?
Thanks, Jerry. Located just a couple of kilometers back from the launch pad itself on the Lluvia Peninsula. This peninsula is culturally significant to local Māori people with ancestral ties to the land, so I want to acknowledge first the Mana Whenua, or the local people, for today's historic launch. Now, within range control, along the back row of the control center, starting from the right of your screen and moving left, sits 2 of our photon engineers managing the spacecraft's tank and communications, and our IT support engineer. Across the aisle is our senior launch conductor supporting the flight director based out of Mission Control of Auckland. Next to them are 2 engineers responsible for the health of the Electron rocket's engines and its reaction control systems. Their full names are Prop and Stage. So in front of them sit the engineers looking after Electron's guidance, navigation and control, and monitoring the state of the rocket's flight computers and software. Along the front row sits our GCs, or ground control operators, who monitor the launch pad's ground systems. And to their left on the right, Mission Control here on your screen, this hub is in Auckland, and it's home to our engineers and technicians whose focus is on our Photon and Lunar upper stage, and with eyes on Photon's Hyper-Curie engine. Behind them, starting closest to the camera and moving right, we have the guidance, navigation and control engineers who are across Photon and Capstone's path to the moon. Their cool name is Fido. In the middle sits spacecraft engineers supporting Photon's communication software, and on the end sits Space Ops software, ensuring our telemetry makes it from the Photon spacecraft to the operator. Then our team lead, responsible for our hardware simulation platform called HITL, which we use to simulate multiple flights to orbit before each mission we launch. And next to them sits Tank, which monitors Photon's fluid systems to ensure its hypercurie engine is provided with its propellants. And finally, at the end of the row is our Director of GNC, Dr. Jonathan Curry. So with that, we are now at T-minus 38 minutes and counting, and proceeding comfortably with the countdown to liftoff. A quick reminder that launch today is set for 9:55 p.m. New Zealand time, 9:55 a.m. UTC. Over to you, Daryl.
All right, thank you, Marielle. It'll be 5:55 a.m. Eastern time as well. Joining me now is Ali Luna, project manager for NASA's Small Satellite Program. She's here to talk about why CubeSats like Capstone are proof that small satellites can have a big impact. Thanks for being here.
Well, thank you for having me today.
So why would NASA choose a small satellite instead of a large one?
Well, I mean, the reason why we choose small satellites is to be able to understand the risk of the missions that we're trying to develop, and small satellites actually gives us the benefit of doing, taking bigger risk. And so having the small satellites being able to, utilize and develop the technology for the bigger missions like the Gateway, is one of the reasons why we choose the Capstone.
And so what are the most important factors when you go to design a small satellite?
But definitely, I think it's going to be understanding the mission architecture, where you're going, understanding the requirements, the environment, and trying to develop that technology so you can infuse it later into the bigger missions.
It's fascinating to hear about how NASA is working with small businesses and these small satellites to get big jobs done. What are the biggest technological advancements you've seen in small satellites?
I think the beauty for small satellites has been that not only are we able to develop the technology really fast and quickly, and mature it, but also being able to now do a Pathfinder's missions like the Capstone is going to be for the Gateway. And so that actually gives us a lot of benefits because we can turn around and really develop and mature that technology.
Which will help the mission behind us right here, which is the SLS not launching today, but a beautiful shot on the pad. We've got two different rockets on two different pads in vastly different locations. On a more personal note, Ali, I was reading an article about your personal journey here, and it begins with an 8.0 magnitude earthquake in Mexico City back in 1985. 5,000 people killed. Devastated Mexico City, where you were born and raised before you came here. Tell me a little about your personal journey and how that sparked you and your mother's journey here to the United States.
Well, definitely, I mean, it's a long story, but just to make it short, when the earthquake happened, my mother, had 4 children. I was the oldest one of 4, and she did not really had a well education. So for her to be able to survive, in Mexico at that time, it was not viable. So she decided to move to the United States and, move with her 4 children. And I was, the oldest one. So I moved with my mother here, and, I had to learn the culture, understand, learn the language too, right? And then be able to get adjusted to this new world. And, it took me some time, obviously, like anybody,
you went to school?
A degree, to be able to have them, to have a better life. And for me, going back to school was the drive. And so I did it, and I graduated. And then when I was graduated, my professor actually told me there's an internship at NASA. I ended up, working at NASA, not thinking that was the path that I was going to take. But, I'm here, and I'm really happy to be here.
How about that? What an inspiring story, Ali. Thank you for sharing it with us, overcoming all those hardships to be here at NASA.
Thank you.
Good luck on the launch, and thank you again for being here. Well, we showed you how Capstone is a Pathfinder mission for NASA's Lunar Gateway. As NASA astronaut Randy Bresnik will show you, the planned orbiting lunar outpost is the first step to fulfilling plans for a more permanent presence on the moon.
Home. For me, home is where my family is. But there have been times in my life where I was called away from my family for extended periods of time. While I was serving in the Marine Corps, it was hard to be away from my loved ones. But thankfully, I had my squadron family, but other places where we were stationed around the globe became a temporary home. Then, in 2009, I launched the International Space Station, traveling even farther away from my family, conducting science 250 miles above the Earth. The space station was an orbiting home for my crewmates and myself. Talk about a room with a breathtaking view. With Artemis, NASA will send the first woman and the first person of color to the moon. We are going there for the benefit of all here. We'll need a place to orbit around the moon, where we can live and work, a place to get ready for our lunar surface expeditions, and a place to return to when our work on the lunar surface is complete. We need a lunar home away from home. This will be the gateway. Starting with the power and habitation modules, the gateway will be the first long-term outpost in lunar orbit humans have ever had. Primed for new discoveries, this orbiting laboratory will provide us with a unique view of our solar system, and it's already becoming a beacon for the future of international and commercial cooperation in space. With increasing capability and longer missions over time, the gateway will be a powerhouse of technology and science, paving the way for future human missions to Mars. Design and fabrication of gateway elements by NASA and our international partners is well underway around the world right now. Wherever you are on planet Earth, today you are part of the Artemis generation. I'm NASA astronaut Randy Bresnick, and I invite you to join us by following NASA Gateway on social media and telling us where you call home.
T-minus 31 minutes and counting until launch in New Zealand with our NASA Mega Moon rocket here on the ground as a backdrop. It's time now to dive into the details of Capstone's orbit, the near rectilinear halo orbit. I spoke to Najib Moranci, chief of the NASA Exploration Mission Planning Office, about it.
Najib Moranci, thank you for being here. We're launching, of course, Capstone today, a microwave-sized CubeSat that's going into this near rectilinear halo orbit. Eventually, it will lead the way for Gateway, a much larger lunar outpost where astronauts will go. What's the difference between getting Capstone into that orbit versus the lunar gateway?
One of the really interesting things with the orbit mechanics is we can sort of play with, how much propellant it takes to get somewhere and the time it takes. So Capstone is using a ballistic lunar transfer, so it'll take 3 months to get to NRHO, but it'll use a quarter of the delta velocity that we'll need when we fly this with Artemis and the crew. So the crew will only spend, 5 to 10 days in transit. We'll fly very close to the moon and use the moon to slingshot us out there, but it takes more delta velocity or relative propellant amount. So we can play with both the time and the duration to get into NRHO based on whether we're flying crew or you're doing something so uncrewed like the Capstone mission.
And looking at this near rectilinear halo orbit, you can see it really goes quickly around the moon, but spends more time away from it. Why is that, and are there advantages or disadvantages to that?
Yeah, so the NRHO, or near rectilinear halo orbit, it's an elliptical orbit. So when you're close to the moon, the spacecraft, any spacecraft will fly very fast. You'll go over the north pole of the moon in about a day, but then we spend about 6 days over the big part below the south pole of the orbit. So you go very fast close to the moon, slow when you're away from the moon. But the reason we're in this orbit is it's incredibly stable, but also relatively close to the moon. So with that stability, we only need the equivalent of 10 meters per second of delta velocity for a whole year to maintain the orbit, which is very small in spacecraft terms. Just the South Pole, we can do the human exploration in the future, as well as have that stability for a good outpost capability. So really it was that balanced orbit for the long-term planning of Artemis and the objectives we need for human exploration.
Oh, that's very interesting. And so what is required in order to maintain that very unique orbit? Is it difficult?
So the orbit should be relatively easy to maintain, but that's why we want Capstone to go first so we can collect all the data and validate the models. So it doesn't really matter what size the vehicles are, the orbit mechanics will work the same. So with Capstone as the sort of pathfinder, It can demonstrate the navigation, the guidance, the propulsive capability to maintain the orbit, and we can really just extract from that the math to validate the orbits for Gateway, Orion, and Artemis missions. So the maintenance of the orbit is really fascinating, easy thing to do, so we can use these two missions to compare how they work. But the other advantages of this orbit is it's very stable for power and thermal and has continuous communication with Earth. So, the operations in this orbit are really good for that long-term deep space exploration capabilities that we want to demonstrate.
Jude Moranci, thank you so much for your time today.
Thank you for having me.
We're incredibly excited to help people stay in.
Before NASA sends their human-rated spacecraft, we want to send our CubeSat Capstone to kind of work out the issues of how do you operate in this type of orbit? How do you do station keeping? How do you do navigation?
Capstone is a pathfinder. Capstone is going to be demonstrating how to put a space station
halo orbit in and around cislunar space, which will provide valuable experience and knowledge for NASA when they operate their Artemis missions.
What I think makes it a really interesting orbit is that it's kind of like balancing a pencil or a pin on the tip. Like, theoretically you can, but you never actually can.
At its core, CAPS is a peer-to-peer navigation system.
So CAPS is the cislunar autonomous positioning system, and we'll be using that to sort of do autonomous lunar navigation in addition to demonstrating the near lunar halo orbit for NASA.
CAPS enables a future where many spacecraft can talk to each other, and they can help each other navigate, figure out where they are, avoid collisions, carry out their objectives, etc.
Instead of talking to the ground, we can talk just directly with LRO and determine where we are in space, determine our position and our velocity in space.
You don't just know that you are X kilometers separated. You can actually estimate the full six-dimensional state of both of those spacecraft. People have shown that mathematically for probably 15 years at this point, and this will be the first time that we actually get to demonstrate it in space.
Going to the moon is about learning. It's about learning how to operate in deep space without a whole lot of support from the ground.
I think it's very cool that we're going to put people back on the moon, especially because when I was growing up, that wasn't a big thing. It was a big thing we had done, but not a big thing that we were doing. And so I think it's really cool to be part of the generations that are bringing that back.
Space travel is kind of like sea travel was.
An exhilarating 2.5 years of developing a foundation for the permanent return of humanity to the moon, and a starting point for us to explore the rest of the solar system.
Well, you heard from the Advanced Space engineers. Now you're seeing them live. This is at Advanced Space headquarters in Colorado, where the Capstone Mission Operations Control Center is. They will jump into action 6 days from today. That's when the spacecraft separates. The Advanced Space team will then assess Capstone's orbit, operate the payloads, and communicate with Capstone through NASA's Deep Space Network and Terran orbit. Back out to the pad, T-minus 24 minutes and counting. Here's a quick overview now of the launch preparations, what we can expect in the final minutes of countdown.
The countdown to launch is the most closely watched clock in mission control. Here are some of the things that take place at each milestone after the countdown begins. At T-minus 9 hours before launch, our crew are on site at Launch Complex 1 to configure the pad for launch and prepare to power on Electron for the day's operations. Meanwhile, our operators in mission control start checking into their stations. At T-minus 7 hours, our operators will brief the launch director with a status update. Mission Control also receives its first weather check on what to expect at liftoff, including cloud cover and predicted wind speed at Launch Complex 1. Now, at T-minus 6 hours, our ground tracking stations begin to power up before Electron is prepared to go vertical on the pad. Soon afterward, Electron's Rutherford engines are tested with a short burst of engine fire to confirm all systems are operating as they should. At T-minus 5 hours through T-minus 3 hours, our range safety team runs through safety status checks for those on and around our launch complex on the peninsula, making sure the team and the public are kept safe during the day's launch attempt. Fuel loading of kerosene will soon begin on Electron, while additional vertical systems checks take place and the pad is evacuated. It's T-minus 3 hours now, and soon liquid oxygen will begin to flow into Electron. As the rocket slowly fills with this oxidizer, Electron's black body turns white as humidity in the air around the rocket freezes into a thin sheet of ice due to the freezing temperatures of the liquid oxygen inside. With 1 hour left to launch, it's crunch time for our operators. Vehicle cameras are switched to their launch settings. Our avionics team enables Electron for flight. Our final weather brief comes through, and the range safety status will confirm that the area is clear for launch. With 12 minutes left in the count, our launch director runs the go, no-go poll with our operators to make the final decision to proceed with the launch. All final checks are completed before we reach T-minus 2 minutes in the countdown. At this critical point, the countdown auto sequence begins and Electron's flight computers take over. The launch director begins counting down to liftoff from T-minus 10 seconds before the engines ignite 3 seconds before launch, and Electron lifts off the pad at T0 on its way to complete its next mission with the satellites on board.
For a big mission. Well, Capstone is flying on a small rocket, but it has a long journey to get to the moon. A key technology that will get Capstone there is the third stage of the Electron rocket called Photon. Let's head back down to New Zealand and join Muriel for more on that. Muriel?
Thank you, Daryl. So to get the spacecraft out of low Earth orbit and on a ballistic lunar transfer to the moon, for the first time Rocket Lab is using its lunar configuration of our Photon spacecraft bus. Now, unlike the Apollo lunar missions of the 1960s and 70s, which took a free return trajectory to the moon, a fuel-efficient ballistic lunar transfer makes it possible to deploy Capstone on a distant orbit using a small launch vehicle. The first 9 minutes or so of the mission will follow the typical mission profile of an Electron launch. The rocket will complete liftoff, first and second stage separation, and finally end with Photon separating from Electron's second stage in an elliptical orbit. Now that is where things start to get interesting, because once separated from Electron, Photon will carry out a series of orbit-raising maneuvers using its Hypercurie engine, stretching its orbit into a prominent ellipse around Earth. About 6 days after launch, a final burn from the Hypercurie engine will accelerate Photon to 24,500 miles per hour, enabling it to escape low Earth orbit and set Capstone on a course for the moon. Within 20 minutes of the final burn, Photon will release Capstone into space for the first leg of the CubeSat solo flight, and then Capstone's journey to NIHO is expected to take around 4 months from that point. Now, once successfully inserted into the orbit, Capstone is expected to remain there for at least 6 months, allowing NASA to study the orbit's dynamics. Now, here are 2 pivotal members of our Photon team to explain more about our Photon lunar upper stage.
My name is Ehsan Mosley. I'm the Chief Engineer for Space Systems at Rocket Lab.
I'm Rich Hunt and Flight Dynamics for Capstone, and I combine all that into a picture of what Photon and Electron are, and use that to design and optimize trajectories to get us from LC1 to putting Capstone on a ballistic lunar transfer to the moon.
It's the most unique mission I've worked on at Rocket Lab so far. We've taken our Electron kick stage and turned that into a full functioning spacecraft, added a lot of delta V to its capability in order to be able to deliver the Capstone vehicle into this high energy orbit.
Traditionally what they did is they'd line it up right and they'd burn in one direction for a very long time to get the energy they needed to basically put them on a translunar injection or a translunar orbit. That is less efficient if you have a lower thrust engine. The way to get around that is to simply split that burn into multiple burns over the course of several orbits. So rather than build your orbit from circular to a translunar injection in one go, you build it from circular through a series of successively more eccentric orbits through a number of burns. So rather than one, like Apollo, we're doing 8 burns to build up our translunar injection. And the cool part about the initial phase of the mission, even though it's on day 1 of 6, is the T0 that we launch into will set our right ascension, one of the orbital elements that defines our orbital alignment. And as soon as we launch into that orbital plane, our right ascension at our payload deployment 6 days into the mission is set. And then 10 minutes later, we'll do our first Hypercurie maneuver which will set the line of apsides, which is another measure of orbital alignment. So then 2 of the alignment parameters are set within the first 20 minutes of the mission. So we need to set them really accurately so that they'll drift onto a moving target, to then hit a moving target, which is the moon, kind of 3 months later. When the mission ends for everybody else, I expect we'll be trying some zero pressure, deep space maneuvering to test our comm systems and our propulsion system and our assisted navigation for other missions like Venus.
I'm really proud of the technology we developed for this mission, but I'm most proud of the fact that this technology extends to future missions for Rocket Lab and NASA, such as our Mars Escapade mission.
We are coming up soon on the go, no-go poll, one of the final gates we need to pass through for Electron and Capstone to leave the pad for today's mission to the moon. Our talented and dedicated team have been making their way methodically through launch pad, range and vehicle preparations in the hours before liftoff. So to confirm we are proceeding all the way through to launch, let's listen in to mission control for that final go, no-go poll. That will be coming up in just a few moments, and we'll keep our fingers crossed for some very good news there.
From this time, the 3-word procedure is in effect.
And there we go. That is a clear run through status checks. And as you heard, we are moving forward to the launch of the Capstone mission to the moon. Our T0 launch time remains 9:55 p.m. New Zealand local time and 9:55 a.m. UTC, or 5:55 a.m. and 2:55 a.m. Eastern and Pacific. So let's go back to the Kennedy Space Center in Florida, where Daryl is with another special guest.
Thank you, Muriel. Got all the times covered. Appreciate that. Joining us now is Justin Treptow, Deputy of the Flight Opportunities and Small Spacecraft Technology Programs, to talk about how small businesses played a large role in this mission. Justin, great to have you back. You used to work here, spent 10 years here.
Yep.
You're now up at headquarters, but back in Florida for this launch.
Absolutely. I'm extraordinarily excited to be here for our lunar mission.
First question, why does NASA partner with small businesses like the ones that were involved in the Capstone mission?
Well, it's an interesting interplay between government and commercial companies. With the spacecraft getting smaller and more capable, we're seeing more entrants getting into the space industry. And as they get more and more experience on orbit, they're demonstrating real capabilities that NASA can partner with to lead missions like Capstone and really take a leading role in gathering data that we can use for other projects. This spools into the ability to have those companies turn those capabilities into services that you can buy as another government organization or other parts of NASA. We heard an interview with Rocket Lab earlier talking about their Escapade mission. They developed the lunar photon, which is being used for another NASA mission, which would not have come to pass if it wasn't for the Capstone mission. We wouldn't have the data for Gateway to take advantage of if Advanced Space wasn't here as a commercial partner on this project to bring the data from one project to another project.
That's fascinating. So you mentioned some of the benefits already that have been gained, and we've seen that through the development of Capstone, right? Because NASA says, hey, go develop this, and then if there's spin-offs that are beneficial in other areas, you're starting to already see that with Capstone?
Yeah, absolutely. Some of the examples, like one of the most obvious ones, is within the Capstone propulsion system itself. Having a high delta V propulsion system on a CubeSat form factor is something that is, in the small sat world, kind of the holy grail. Being able to go somewhere and actually do something of value is really useful. And having Stellar Exploration develop a propulsion system that Capstone's using to get into orbit around the moon in the NRHO and to stay there for an extended period of time is a propulsion system that's showing up in other commercial products that's infusing within the industry. So we're seeing the technology that NASA's funding for our missions go into other places within the space industry.
Already, so quickly, early on in this. That's impressive. We're now T-minus 10 minutes and counting until the liftoff of Rocket Lab's Electron rocket. I want to ask you about a previous Rocket Lab mission that NASA did. You're familiar with it, Alana 19, as part of the Venture Class Launch Services Initiative. What was the benefit of that, and what did we learn from that we're moving into this mission?
So the initial Alana 19 flight was a Venture Class Launch Service. Rocket Lab was a very new entry to the launch market at that point. NASA wanted to get an opportunity to work with them on a project. And what we learned from that is that companies like Rocket Lab, like Tyvak, the bus supplier, for this mission, they're very capable bringing their commercial best practices to the table and are able to really lead missions and projects. So it has, Alana 19 and the Venture Class Launch Service was this first stepping stone to getting into these more advanced missions where our industry partners, again, are really taking a strong lead in the overall mission.
And briefly, Justin, give me a sneak peek at what's coming down the line. Any exciting partnerships with small businesses similar to this Capstone mission?
Yeah, so in the near future, we have a number of other CubeSats that are in the work. They're also going to be doing big technology demonstrations in small packages. We have Lunar Photon also going to the moon to shine a laser into the permanently shadowed craters of the moon to look for water. We have a Starling constellation of small spacecraft that is going to be doing on-orbit networking demonstrations and interfacing with other commercial partners on orbit, helping to alleviate conjunctions and to make space easier to access for all participants.
Justin Treptow, thank you very much, and welcome back.
Thank you very much, Darren.
A quick programming note before we go back down to New Zealand. I want to let you know that later this morning, Northrop Grumman's Cygnus spacecraft will be departing the International Space Station at 7:05 a.m. Eastern Time. We will have live coverage here on NASA TV starting at 6:45 a.m. Eastern Time. Again, Northrop Grumman's Cygnus spacecraft will be departing the International Space Station at 7:05 a.m. Eastern Time. All right, let's head back down to New Zealand. We are T-minus 8 minutes and counting, and Muriel Baker with the countdown.
Thank you, Daryl. It is T-minus 8 minutes and 10 seconds until liftoff. If you're just joining us, welcome to Rocket Lab's Mission Control Center in Auckland, New Zealand. Things are looking great so far for an on-time launch today from our private orbital range, Rocket Lab Launch Complex 1 on New Zealand's eastern shore. Now, you have seen the launch range and inside our mission and control centers. Now it is time to get you acquainted with the Electron rocket lifting off the pad today. And as you will have seen earlier in the show, we are taking an unconventional path to the moon, and that is because Electron is an unconventional rocket, the first of its kind in many ways, and one of the smallest orbital rockets in history to attempt to launch a spacecraft to lunar orbit. So here's a little bit more on Electron.
A small launcher dedicated for small satellites, Electron was the first of its kind to reach orbit when it first took to the skies in 2017, opening up access to space for small satellite operators. Today, it is the second most frequently launched U.S. rocket annually. More than 140 satellites have found their home in space across more than 24 Electron missions launched from Rocket Lab Launch Complex 1, the world's first and only private orbital spaceport. Designed, manufactured, and launched by Rocket Lab, Electron is a two-stage launch vehicle powered by liquid oxygen and rocket-grade kerosene. Much of its structures are made of advanced carbon composite material, including its propellant tanks, which is what gives Electron its sleek black look. The rocket is powered by 10 Rutherford engines, 9 at the bottom of the first stage, and a 10th space-optimized engine to power the second stage to orbit. The Rutherford engine is the world's first to use an electric pump feed cycle for orbital spacecraft, making use of electric motors and batteries to drive its propellant pumps. It's also 3D printed using additive manufacturing processes. Electron is also equipped with a third upper stage that serves as in-space propulsion to deploy payloads to orbit. In its most advanced form, this stage is called Photon, a spacecraft bus to support small satellite missions even beyond Earth orbit. It's to this structure that the Capstone satellite is attached, ready to be carried on its way to its lunar destination and near rectilinear halo orbit.
T-minus 5 minutes and 30 seconds on the clock, and from here the launch team will move on to some of the final milestones and checks of Electron, Photon and Capstone before liftoff. The mission will launch from Pad B today at Launch Complex 1, where we have 2 orbital launch pads within our private spaceport dedicated for Electron launches. Now, Rocket Lab launches typically deploy spacecrafts to orbits between 500 and 1,200 kilometers altitude above Earth's surface, but this time, as you'll know, Electron and our upper stage Photon will send the Capstone spacecraft a little bit further than usual, some 1.3 million kilometers further. Around 9 minutes after liftoff, Electron's second stage will separate from Photon, placing the spacecraft bus and its Capstone payload into an initial low Earth orbit of just 165 kilometers. Now, from this initial parking orbit, Photon's Hypercurie engine will perform a series of orbit-raising maneuvers over 5 days to stretch its orbit into a prominent ellipse around Earth. Now, 6 days after launch, Hypercurie will ignite one final time, accelerating Photon to allow it to escape low Earth orbit and set Capstone on a course for the moon. From there, Capstone's journey to NRHO is expected to take around 4 months, with the CubeSats team at Advanced Space's Mission Operations Center commanding the spacecraft to fire its thrusters to adjust its course accordingly. Now, if we are looking back at the pad camera now, we can see that the rocket's strong back has retracted and has moved into the launch position. This launch platform structure is what holds the umbilical lines, providing power to the rocket, which will fall away as Electron lifts off the pad. You can see Electron's icy white stripes on the outside of the rocket there too. Those are because of the super cold liquid oxygen propellant on the inside of the rocket, which freezes water on the outside, causing it to form those distinctive icy areas along the rocket's black carbon composite body. Now, our last weather update also confirmed that the wind speed at T0 is expected to be good for launch, further minimizing the weather risk to today's mission. Now, as we get closer to the countdown, it is worth pointing out what kind of views to expect from launch today. As always, we'll be bringing you the live views you see on your screen from various cameras at the pad and at range control. However, for this mission, we won't have the typical onboard vehicle cameras you might be familiar with for Electron launches, and that is because this mission has extensive telemetry requirements. So to reduce the load on systems and operators, we've streamlined the mission down to essential systems only. Now, while we won't have those live vehicle feeds to show you, we will be broadcasting mission data and animations so you can keep up with the launch progress throughout the ascent. And now we are coming up to a critical juncture in the lead up to launch, the switch to the countdown auto sequence. The team are tracking no issues with the launch vehicle, Capstone and Photon remain healthy, and the weather is looking good. So at T-minus 2 minutes, very shortly, that autonomous flight computer on Electron will take over the launch countdown, followed by the call that LOX loading is complete on Electron. Then at T-minus 1 minute, we can expect confirmation that the vehicle's first and second stages are pressurized for launch. So, followed by that will be the iconic final countdown to liftoff at T-minus 10 seconds and engine ignition at T-minus 3 seconds. We'll hand over now to Mission Control and listen into those calls to launch.
Helium anti-gas disabled.
Stage 1 and stage 2 addressed.
High flow engine purge enabled.
Entering burnout detect mode.
Crankshaft runway.
At T+1 minute and Electron is in the air and onward to the moon for the Capstone mission. That rocket is soaring through this nighttime sky, now past 14 kilometers in altitude in these past few moments. Now things look to be continuing nominally, which means that shortly Electron will come up against